We are good to go. We are live streaming on our Facebook handle. I request Dr. Ashish Ratan Mishra to start the proceedings.
Okay, thank you. Engineer Leslie. Good morning, everyone. Thank you for being here this morning. We are going to start our webinar now. But before we start, I would like to request our University Chaplain, Reverend Dr. Samuel Richmond Saxena ji, to lead us in our opening prayer.
Thank you, sir. As we begin this webinar, I would like to read from the Bible the very important verses that is found in Genesis chapter 1, verses 1 onwards. In the beginning, when God created the heavens and the earth was formless, void, and darkness covered the face of the deep, while a wind from God swept over the face of the earth. Then God said, "Let there be light," and there was light. And God saw that the light was good, and God separated the light from the darkness. God called the light day, and the darkness he called night. And there was evening, and there was morning the first day. Let us look, our Lord, in prayer. Our gracious Heavenly Father, we are thankful and grateful to you once again that you have given us the opportunity to be together, and especially Sam Higginbottom University of Agriculture, Technology and Sciences, under the Center of Geospatial Technologies, is able to organize webinar on geospatial technologies for managing agriculture. We are thankful, Lord, that you have really blessed our university, that's why we are able to organize international webinars. And we know, Lord, that the university is making great contribution even in the midst of COVID-19. We pray for the success and the blessing upon this particular webinar, which has been organized. And we pray that, Lord, you take control of everything. You take control of the technology that is helping us to be well connected. We pray for all the participants who will be joining this particular webinar for 2 days. And we are sure that through this webinar, most of our participants will be blessed. We are thankful for the eminent speakers who have joined us today, and they will be joining also tomorrow, some of them. We pray that your blessing be upon them as they share from the expertise. Our students, participants, faculty members be equipped in this particular area. We are thankful for the chief guest, Professor Lawrence, who is here with us. And as he will be sharing something very important and relevant related to the topic, we pray that we all be blessed through that. We are thankful for the organizing committee, especially we are thankful for the Dean. We are thankful for Professor Dr. Deepak Lal, who is coordinating and organizing the whole program along with the faculty members. We pray that your blessing be upon him. We also pray for Engineer C.J. Wesley, as he always helps us in organizing such a wonderful webinars that we have seen from last many days. We continue to pray for our university, that your blessing be upon our university. We are thankful for our Honorable Vice Chancellor, under whose leadership the university is growing, and many people are being reached through this. We pray for all our officials. We pray for all our staff members, professors, teaching, non-teaching staff, as well as students, that through this great university, which has been founded by Dr. Sam Higginbottom, we all be blessed. We are thankful, Lord, that you are a creator. You have created the earth so beautifully, and your eyes are fixed, and you know every location where the needs to be provided, and you try to do uh, best for us when we are in need, and you protect us. Once again, we are thankful and grateful to you for this wonderful time and opportunity. We ask your blessing. In Jesus' name we pray. Amen.
Thank you, Dr. Saxena. Now I would like to welcome our guests, speakers, and participants on behalf of our Center for Geospatial Technologies of WOG Institute of Agriculture, Engineering and Technology. First, it is my privilege to welcome our Honorable Vice Chancellor, Most Reverend Dr. Arbil Sir, for his vision and leadership. It is my pleasure to welcome our Chief Guest, Dr. Vishnu Chandra, Deputy Director General and Group Head of Remote Sensing and GIS at National Informatics Center, Government of India, for giving his valuable time and support to this seminar. Now I would like to welcome our Pro Vice Chancellor, Academic Affairs and Quality Assurance, Professor Dr. A.K.A. Lawrence, for his continuous guidance for conducting this webinar during this difficult time of COVID-19. Please welcome with me our Pro Vice Chancellor Academics, Professor Dr. S.B. Lal, for his continuous support for conducting this webinar. I would like to welcome our Pro VC Planning, Monitoring and Development, Professor Dr. S. Herbert, for his moral support. Now let's welcome Registrar of University, Professor Dr. Robin L. Prasad, to facilitate the smooth conduct of this webinar. Please welcome our Joint Registrar of SHUATS, Engineer C.J. Wesley, for providing all the technical support for this webinar with his team. Now, I would like to welcome Professor Dr. Ashok Tripathi, Dean, WOG Institute of Agriculture, Engineering and Technology, for his continuous support. Last but not least, from our University Authority, let's welcome Professor Dr. Deepak Lal, Head, Center for Geospatial Technologies, for his leadership in conducting this webinar. Now, I would like to welcome our guest speaker, Dr. Daniel Zakaria, Agriculture Water Management Specialist at Department of Land, Air and Water Resources, University of California, Davis, USA, for giving his valuable time even though it's late night in USA. Please welcome Dr. S.P. Agrawal, Group Head of Water Resource at Indian Institute of Remote Sensing, ISRO, who is our alumnus of SHUATS, for giving a concern to give a lecture on this webinar. I would like to welcome our guest speaker, Dr. Manjul Hajarika, Director, Geoinformatics Center, AIT, Thailand, for giving valuable time from his busy schedule. Please welcome Dr. Harikishan Jayanti, Consultant Agriculture, Remote Sensing, Irrigation and Water Resource and Risk Analysis at United States Geological Survey, USA. Dr. Tapan B. Pathak, a specialist in climate adaptation in agriculture at UC Davis, Merced, California. And Dr. Juan Miguel Ramirez Cuesta, Remote Sensing and GIS Specialist at Spanish National Research Council, Spain, for giving a concern to give presentation in this webinar. Last but not least, our participant of this webinar, whose zeal to acquire knowledge motivated us to conduct a webinar on geospatial technologies for managing agriculture application from USA, Europe, and Asia. Hope it will open new horizon of knowledge for you all. Thank you. Now, I would like to request Professor Dr. Deepak Lal Head Center for Geospatial Technologies, to enlighten us about the webinar and vision of our center.
Thank you, Dr. Ashish. Maybe I would just like to request Engineer Wesley to give me screen sharing, please.
Dr. Deepak.
Yes. Um, well, once again, welcome you all to this webinar, and we are very happy to see all our speakers and all our dignitaries to be present at this time. I would like to briefly tell about the webinar, where the main intention and the main aim was to gather the speakers from the major agricultural areas of this entire world, where we can see technology applications such as remote sensing and GIS in agriculture. And as well as the most important part is how we are collecting the ground data, because we know that remote sensing and GIS techniques, they can help us to reach larger areas. We cannot have so many ground measurements and ground data in large areas, but we can only have in representative areas. So we need some more technology to collect
Dr. Deepak.
Sound is not coming.
Yes, Dr. Deepak.
Okay, by the time I would like to invite our colleague, Engineer CJ Wesley, Joint Registrar of SHUATS, also co-convener for this webinar, to give brief sketch of our university. Dr. Wesley.
Thank you, Dr. Deepak. So, Ashish, uh, good morning. Respected Chief Guest for today's webinar, Shri Vishnu Chandra, the DDG National Informatics Center, Government of India. Our Pro Vice Chancellor Academics, Professor Dr. A.K. Lawrence. Dean, Wow Institute of Agriculture, Engineering and Technology, Professor Dr. Ashok Tripathi. The Head Center for Geospatial Technologies, Professor Dr. Deepak Lal. Our distinguished speakers of this webinar, and my dear participants. Sam Higginbottom University of Agriculture, Technology and Sciences, earlier known as Allahabad Agriculture Institute, AAI, was established in the year 1910 under the leadership of Dr. Sam Higginbottom, an American scientist. The institution has completed now more than 110 years of dedicated and relentless service to the nation, with its vision and mission, gospel and plow, and motto, feed the hungry and serve the land. Under the dynamic leadership of our Honorable Vice Chancellor, Most Reverend Professor Rajendra Bilal, Allahabad Agriculture Institute, once an institute under Allahabad University, was conferred deemed to be university status by the Ministry of Human Resource Development, Government of India, in the year 2000. It was later renamed to honor the founder during its centenary year, that was to 2010. The institute, the deemed university, was renamed as Sam Higginbottom Institute of Agriculture, Technology and Sciences, deemed to be university by MHRD, Government of India. In the year 2016, after considering the adequate availability of teaching, non-teaching staff, and other essential infrastructure facilities, the UP legislature decided to upgrade, reconstitute, and establish the deemed university as a full-fledged state university under State Act. Hence, now we are called as Sam Higginbottom University of Agriculture, Technology, and Sciences. SHUATS is a united endeavor of Christian community in India for promoting rural life and development in conformity with the Christian vision of humankind and the creation. The university is held in trust as a common ecumenical heritage by the Christian churches and Christian organizations of the country. It seeks to be a national center of professional excellence in education and service to the people with the participation of students and faculty members from all over India and abroad. University operates with faculty of agriculture, engineering and technology, sciences, business studies, theology, animal husbandry, humanities, film and mass communication, and health sciences. University operates strive to prepare its students to take the right places as farm managers, agriculture scientists, officers, extension workers, managers, educationists, agriculture administrators, scientists, biotechnologists, microbiologists, biochemists, engineers, software professionals, theologians, and pharmacists, and much more. Schwartz is an ISO 9001 2015 certified institution, a recognized member of Association of Indian Universities, Indian Agriculture Universities Association, All India Association for Christian Higher Education, Association of Commonwealth Universities, Asia Pacific Association of Agriculture Research Institutions, APARI, Global Consortium of Higher Education and Research for Agriculture, Trust for Advancement of Agriculture Sciences, Global Forum on Agriculture Research, Asian Association of Agriculture Colleges and Universities. University has signed many MOUs with national and international reputed institutions. The UGC placed our institute when we were deemed university in the year 2013 among the A grade universities in the country. In the year 2014, National Accreditation Council (NAC) accredited us with A grade, and Naini Agriculture Institute of our university is accredited with accreditation by Indian Council of Agriculture Research, New Delhi. Currently, we have over 13,000 students pursuing their higher studies on campus at SHUATS with more than 500 teaching and 1,500 non-teaching faculty members from all over India. With these words, I would like to welcome you all on behalf of our university and wish you wonderful experience through this international webinar today and tomorrow. Thank you. Over to you, Dr. Mishra.
Thank you, Engineer Wesley. Our talk with our head, Professor Dr. Deepak Lal, was interrupted. So I would like to invite again to start his conversation. Dr. Deepak Lal.
Yes, so sorry, I got disconnected. So in short, this webinar, through this webinar, we are aiming to showcase the technologies, particularly remote sensing and GIS, in agriculture, how we can manage one of the most important aspects like crop monitoring, irrigation, and yield prediction, and how we can integrate the ground data, and how we can use these integrations to towards the betterment of agriculture. And just to talk about our center, the Remote Sensing GIS Center, which we call it as a Center for Geospatial Technologies, I would like to request Wesley to give me a screen sharing. Please, if Wesley can give me a screen sharing, I can just show you a few slides. That will be better.
Yeah, please go ahead, sir.
Yeah, thank you. So yeah, I mean, the Center for Geospatial Technologies, which is organizing this webinar, I would just like to go through quickly with our goals, with our structure, a very brief introduction of our faculties, the activities that we do here, the programs that we offer, a brief introduction about the alumni and future prospects. So one of the goal and most important goal is to be a central facility and channel for disseminating the information on remote sensing and GIS. Then our goal is also to do a lot of collaborative work by MOUs and MOAs through various universities, agencies, and centers, and any other organization which is interested in doing collaborative work and research on remote sensing and GIS. Then we are also interested in doing interdisciplinary research work and diversified research, as well as teaching. Then our goal is also to conduct training and offer services and capacity building. Then we also do a geodatabase building of remotely sensed data such as satellite images or GIS data that can be utilized further. And then another goal that we focus on is to provide support to our state division and directorate of development in their various tasks, like when they are planning something or they are doing some civil work, then how we can provide them a tech support through GIS. Let's look at the structure of the center. So we have divided the entire center into small units, which can specifically focus on research in particular areas such as agriculture. So the unit of agriculture focuses on application in agriculture science, agriculture engineering, meteorology, and other related streams. The unit of natural resource management focuses on our natural resources such as forestry, resource management, watershed management, and then unit of applied sciences, of course, in geography, forensic science, health science, and then unit of engineering technology in streams such as civil engineering, computer science, electronics, and other related streams. Then the faculties, myself, Deepak Lal, I'm blessed to have this opportunity to head this center. Then we have Dr. A.R. Mishra. He has done his MS from University of Arkansas and PhD from University of Florida. He's working with us in the capacity of associate professor. Then we have C. John Wesley, who is working in the capacity of assistant professor selection grade. And he's also involved in university administration as the joint registrar. Then we have Mukesh Kumar, who is working with us in a capacity of assistant professor. He holds an MS from Europe and PhD from SHUATS. And then we also take the help of Shakti Shurevanshi, who is essentially an assistant professor in the Department of Civil Engineering, but we collaborate with him a lot. So I thought it would be only appropriate to show his profile as well. So we have a group of quite experienced people who are always passionate to deliver teaching and research in remote sensing and GIS. So let's see some of the activities that are ongoing. So we are basically conducting research, teaching, and training in the field of remote sensing GIS. We also offer courses of remote sensing GIS across the various schools and departments within SHUATS, such as forestry, agriculture, and Department of Civil Engineering. We are also involved in interdisciplinary research, so the students from other departments can come and do their research. They can apply this technology, they can learn about this technology, they can also implement in their thesis. Like one of the PhD students was from forensic science, she used a lot GIS. Then we have students from other departments as well. Then we are also a nodal center for the outreach programs that are run by Indian Institute of Remote Sensing from ISRO, Government of India. The programs that we offer this is the option with thesis and report. MTech for 2 years, 4-semester program. MSc 2 years, 4 semester. Then we have PG diploma 1 year. This is mostly for professional people or who would like to add something quickly. And then of course PhD 3 years, 6 semester. Then we also offer customized certificate training courses depending on the need and requirement. And then we have eligibilities for our PG and PhD programs. Basically, it's at least 50% in your UG degree for PG degree, and then PhD, you need a PG degree in relevant branch. I've gathered some of our alumni from last almost 10 years. And as you would see that we are really pleased to see how well they are being placed, how well they are working, how well they have been accepted. And if you would see that there are at least 1 or 2 companies where we have more than one alumni. So that's also a very good achievement where, you know, people are realizing and acknowledging our efforts. So future prospects, I would say the students who graduate from here, they have several options like working with government sectors, remote sensing application centers, government undertaking companies. Then there are private consulting companies, software development firms, manufacturing companies. Then there are purely research posts like senior research fellows and other related positions in various projects. And of course the higher studies, as we have already seen that a few of our alumni have joined PhD in national and international reputed organization and universities like IITs and have gone international as well. So normally the admission, if you have a question about admission, we can talk this about in detail, but here just a brief introduction of our admission process. Normally we would do an all India entrance test, but due to this unprecedented situation, we are doing online counseling. So merit-based online counseling starts July 1st, and the steps are very simple. You can go on the website, and we have only limited seats. We have only 10 seats for our PG program because we believe in delivering quality and we believe preparing a good researchers so that they can work and they can excel. So if you're interested, contact us. Feel free to contact us and join us. And it'll be great to have you all. So thank you. And I give it back to Dr. Ashish Ratan Mishra to continue with.
Thank you, Dr. Lal. Now I would like to request Professor Dr. Ashok Tripathi, Dean, WAG Institute of Agriculture, Engineering and Technology, to enlighten us about WAG Institute of Agriculture, Engineering and Technology. Tripathi sir. Tripathi sir, can you hear us? I think due to the technical problem, not able to connect with Tripathi sir. So it is my privilege to invite our Pro Vice Chancellor, Academic Affairs and Quality Assurance, Professor Dr. A.K. Lawrence sir, for the word of encouragement.
Can I have a screen, please, Bashir? Thank you. Thank you. Good morning, everyone. I'm pleased to be a part of this international webinar series 1 on geospatial technology for managing agriculture, particularly application from USA, Europe, and Asia. It is being organized by Center for Geospatial Technology, Vaughan Institute of Agriculture Engineering and Technology of Sam Higginbotham University of Agriculture, Technology, and Sciences. We are extremely happy and thankful to the Lord for His abundant blessings which He has provided to all of us. We have a long and rich heritage of serving the Lord, the land, and the world. This one-year and professional institution has successfully traveled 110 years. And today, as a multi-faculty state university, it stands as a dedicated and relentless service provider to the state, nation, and to the world. Now, with all kind of privileges, right, and freedom in this world, we are also managing COVID-19 pandemic, which is spreading quickly, causing a great deal of fear and unrest, not only in India, but across the globe. And in spite of this unprecedented crisis, we are very effectively utilizing this time to specifically emphasizing on the use of geospatial technology for managing agriculture. Now, if you focus on agriculture and geospatial technology, I would like to focus on agriculture. And when we talk about agriculture, or when we talk about smart farming, we focus on precision farming, and is therefore a farming concept that utilizes geospatial tech information to determine field variability to ensure optimal use of inputs and maximize the output from a farm. The large area of land usually have special variation. You all know this is about the soil types, moisture content, nutrition availability, and so on. Therefore, with the use of remote sensing and geographical information system and global positioning system (GPS), the farmers can more precisely determine what inputs to put exactly when and with what quantities. This information certainly helps the farmers to effectively use expensive resources such as fertilizers, pesticides, and herbicides, and more efficiently use of water resources we have in our country. And farmers who use this method not only maximize their yield, but also reduce their operating expenses, thus increasing their profits. On these grounds, therefore, it is very important to focus on the use of geospatial technology in precision farming in India, particularly. To achieve this, the paper and every part of progress we are going to do will focus on how this data is collected, analyzed, and used in decision-making process to maximize on yields. The effect of the effort of Center for Geospatial Technology of our university will certainly enlighten the path to overcome the challenge with more opportunities and with a positive outcome as regard to Indian agriculture is concerned, and as regard to our Honorable Prime Minister's aim to double the income of the farmers. I would like to thank the keynote speakers for their valuable time and the other speakers who have joined us for this webinar. I also express my gratitude to Chairperson, Convener, Organizing Secretary for organizing this meaningful event. Thank you so much, and God bless you all. Over to you, Wesley. Thank you.
Thank you, sir.
Thank you, sir. Now I would like to request Professor Dr. Ashok Tripathi once again. Yeah, he got disconnected last time to tell about our Wog Institute of Agricultural Engineering and Technology, its history and others. Dr. Tripathi. Sir, can you hear us? Seems like there is some technical problem with Tripathi, sir. So I would like to start now our keynote speaker. We are pleased to welcome Dr. Vishnu Chandra, a very special guest from New Delhi, India. Dr. Chandra is Deputy Director General and Group Head of Remote Sensing and GIS, Environment, Forest and Climate Change, Power, Energy and Coal at National Informatics Center. He is alumnus of IIT Roorkee and has more than 21 years of experience in remote sensing and GIS. Today, he will be sharing with us his expert opinion on geospatial technology in agriculture. With that, I ask you to full attention with Dr. Chandra and help me welcoming him with his talk. With Dr. Chandra.
Sir, kindly unmute. Dr. Chandra, kindly unmute.
Yeah. Can I share my screen? Should I share my screen?
Please share. Thank you. So presentation mode, please.
Yeah. You're getting in presentation mode?
Yes. Good to
Yeah,
go, sir.
This is my proud privilege to be associated with this webinar. And I thank Vice Chancellor, Professor Deepak Lal, and all organizers for inviting me as a chief guest. I thank Vice Chancellor, and basically, I am, as organizers have introduced me, I am from National Informatics Center and Ministry of Electronics and IT, who are providing national IT infrastructure, and we are extending geospatial service as a part of IT sub-services from NIC. So presentation, my talk outline, initially I will talk about what is NIC, National E-Governance Infrastructure and Services, New India Vision and Digital India. Then I will move for what you call e-agriculture or digital agriculture, followed by Geo-ICT Vision and GIS platform services, which we are extending, and with certain case studies and examples. Because as Dr. Deepak Lal has in his introductory remarks says, how to reach the unreached means many ground level data collection and surveys happens. Unless those content is not mainstreams through IT platform, it will not reach the unreached. And ultimately it has to be converted in a service oriented model so that service delivery can happen. So NIC, and as part of my profile, that kind of services we are extending. So ultimately we are trying to geo-enable various schemes and program of government using geospatial data, remote sensing data, and data comes from various sources. So this is what is the things which we are doing. NIC is what you call trusted technology partner of government. we are providing IT infrastructure on demand, developing, designing IT system for government, and also providing services in new emerging technology areas like AI, data analytics, and blockchain, and so on. We have a complete digital infrastructure covering central government, state government, district government, connecting with a high-speed network called NKN and NICNet, video conferencing infrastructure. These days during COVID time, our video conferencing infrastructure is heavily used for work from home. Now, then data center services, various platform services, including GIS, is extended as part of digital infrastructure. Pan-India network with gigabit speed, with VSAT more than 100 plus, secure access through VPN and secure Wi-Fi services. In fact, your agriculture university SHUAT is also one of the what you call national knowledge network node. NKN high-speed services are being extended there, where over 1700 plus institutes are connected. More than 5 crore researchers and academicians are connected. 35,000 plus virtual classrooms with international global connectivity with CERN, Singapore, Amsterdam, and so many places, with extended connectivity to Sri Lanka, Bhutan, Bangladesh. So this is the reach of national knowledge network, where research and academic community can do a specific project and share their knowledge and data for specific project requirements. We have a number of data centers, national data centers, state data center. We are managing Government of India Cloud, Prayagraj, and for delivery of the services. Large email and SMS services, which becomes integrated various with workflows, is provided by NIC. So most of the government employees, particularly a state government employee, is use our email services, SMS services, for even for giving alerts to farmers. SMS services are being used from NIC. For what you call direct benefit transfer, all kind of alerts goes through SMS to farmers, to unorganized workers, and so on. Large number of video conferencing network and studios to facilitate meetings and interactions and seminars. Now, Prime Minister talks about New India vision. What should be the new India? And there are certain priority areas like to build next generation infrastructure, clean and green India, expanding rural industrialization using modern technologies. For example, agriculture, formal welfare, and food security. Now, all these areas has a geospatial component into it. So ultimately, agriculture cannot be seen in isolation. It has to be seen with respect to, say, infrastructure, with respect to the needs of the farmers and so many things, and technology part of it, which will come from different sectors, startups, industries, and so many things. So this is what focus areas of government in terms of new India dimensions. What are the drivers? Infrastructure, inclusion, and governance. And in this, you see, doubling farmers' income is one of the drivers, which is basically is, if you go in agriculture as a whole, infrastructure requirement for agriculture, what inclusive growth we can do with proper governance model for doubling of the farmers model. This has complete geospatial dimension, which has to be overlaid on ICT infrastructure for delivery of services. Digital India, to empower society and knowledge economy digitally, has a three major focus area, which deals with digital infrastructure as a utility to every citizen, governance and service on demand, digital empowerment of citizen. All these three major areas has requirement for, say, asset mapping, location-based service, to leverage GIS services on demand at grassroots level. So infrastructure mapping, what you call point of interest mapping, school location, health location, your Krishi Vigyan Kendras location, all those infrastructure location should become part of service delivery network. So then only you can overlay and deliver your research as a service to the field unit. So this is what the Digital India program. E-agriculture. Now this e-agriculture system, if you see, end to end, there has to be ICT in use. Now cloud computing is the core information. At top of it, you have to have GIS and drones and UAVs, Internet of Things, breeding informatics for organizing data and information, mobile computing, mobile devices, web analytics, web applications, web GIS and web MIS. Now total portfolio of ICT service and delivery system needs to be integrated with agriculture systems. Now, a lot of talk about, as a domain expert, about agriculture farming systems, which is defined as a population of individual farm system that have broadly similar natural resource base, enterprise pattern, household livelihood, and constraint, for which certain strategies and interventions has to be formulated. Now, if you see that, again, you need natural resource base in terms of water, land, grazing areas, forest, climate information, landscape information, dominant farm activities information. All these components in terms of data and informations are required for agriculture farming systems. Now, these data sets will be collected through various means, and there is a huge role of GIS, and IoT, and data analytics and AI on it. This part, science of where, science of when, and science of what, is part of GeoVision, GeoICT vision, which I am going to showcase in coming slides. Use of GIS in agriculture farming system. You need agriculture technology from a location. Which technology should be appropriate for which agroclimatic zone? How you extrapolate your agriculture research done at certain farm level to larger agroclimatic zone and areas and districts. What kind of data models and analytics and parameters and criteria are required to do that? That is what I'm saying. ICAR talks about farm to lab to farm program. So how you can scale up the research done at lab level for certain farms field and certain agroclimatic or agroecological zone to larger area for district planning, for panchayat planning. That is what the ICT platform can facilitate. Data from machine, what is precision farming? You get directly data from sensors and IoT devices. Data from sky, satellites and drone, that is what is required. Data online real-time mapping. Online means there are mobile apps. People go and collect the data using mobile app. Here, mobile app needs to be designed as per the custom criteria. You can embed your service or sampling schemes for, say, soil sample collection in your mobile app. Whether you are doing for rain-fed area or non-rain-fed area, how the soil samples are collected, that knowledge can be embedded in your mobile app. That app can act as some sort of a survey tool for collection of soil samples and then extrapolating those information out of those soil sample with respect to a soil physiographic unit or what you call soil grid, and creating a thematic scenarios. Now, this is what ultimately, when we talk about today end-to-end systems, I am saying data capture, processing, and delivery of service. All stages of end-to-end system should be integrated seamlessly in a ICT platform. So crops as a location, GIS can be used as a tool. Agriculture's map can be generated. Modeling and data mashup through APIs, through web service can be done on an ICT platform to have an integrated use of agriculture farming system. These are some of the GIS-based multi-layer system for crop inventory, land use management is the requirement. In fact, NIC is providing geospatial platform to integrate data sets coming from various heterogeneous sources and with heterogeneous standards, so that you can mash up the data and create a delivery system for services as per the user's requirement. Use of drone. I will also speak about very recent scheme which Government of India Ministry of Panchayati Raj launched, known as Swamitva, where Survey of India is conducting the drone survey for Abadi area in villages. So that is opening up lot of field for future data integration, where agriculture community can participate to have a agriculture resource management plan, which can be part of Gram Panchayat development plan, and it can be implemented at field level. Now, the Geo ICT vision and NIC's GIS platform Bharat Maps, I will talk about it. See, as we know, geography is a platform by default, by legacy. Before advent of IT or ICT, geography was used to integrate data with respect to common piece of geography from, say, weather, from agriculture crop, and so many, all man-made and natural interaction are organized around common piece of geography. That's why it is known as science of where. So later when computing came and science of parallel processing and supercomputing came, computing is sequential, where science of geography or science of where by default is a science of parallel processing. But with more computing power, more storage, more new emergence of new dimension in ICT infrastructure, today with using supercomputing, it is possible to stream real-time data from various heterogeneous platforms. You can get traffic information through mobile real time. You can get information from rain gauges real time. You can have even real time satellite imagery. So supercomputing is through parallel processing, is integrating on the data on fly, coming real time. So what is happening? Science of where is getting seamlessly integrated is what you call science of when, where IoT sensor and all those things are streaming the data, and science of what, where big data, geoanalytics, all those key integration of AI and ML with GIS, all these things are happening. So this is what, when we talk about end-to-end ICT system, say for agriculture, you have to have from data capture for location, processing it, then analyzing it as a total end-to-end delivery system. An ICGIS platform, which we have built over the period of time, we took the data from various geospatial organizations like Department of Space, Registrar General of India, Forest Survey of India, NRSC, NSDI, and brought it on a common platform, and with all kind of geospatial services which can be consumed real time in various e-governance application projects. So what I'm saying, we have established a GIS cloud where all data is managed and maintained as a single source of information. And from that cloud, we give OGC compliant GIS services, which can be consumed by, say, Agriculture Ministry, Urban Ministry, MHRD, and many other. So this is the way we have created this kind of thing. This whole range, starting from data, GIS base map services, GIS services, geocoding, reverse geocoding services, navigational services are available on our platform. for dashboards, analytics, asset management, thematic applications, natural resource management, routing application. So what I am trying to say is every scale and accuracy is important on a GIS service platform. We have every scale of mapping is linked with type of survey, from say reconnaissance survey to detailed survey. Each scale is linked with what you call level of decision making and type of survey. Each scale is also linked with level of e-governance services. This is how we have designed. When we talk about say transaction services, land transaction services, or sale deed kind of application, then scale should be 1:2000 or higher. When I say project management services, the scale of mapping should be 10,000 scale. When I say urban city mapping, I am talking about 500 scale. Or for master plan mapping, I'm talking about 10,000 scale. So for each level of scale, I am integrating various data with various accuracies to serve various level of e-governance for various level of decision making. So this is what multi-layer GIS platform has been established by NIC. Data came from Survey of India, DOS, various ministries and departments, and NIC has acted as a facilitator, standardization integrator for cloud-based GIS services. This is bharatmaps.gov.in. It is a public platform. You can visualize and see it. Anybody can see it. We have foundation data from multiple sources available on this platform. This is some list available. So we have collaborated with everybody to bring data on a common reference frame on a standard platform so that it can be utilized and served as a cloud-based services to various users and ministries and departments. Complete base map service in 1:50,000 scale from a Survey of India, and 1:10,000 scale for entire country. 1:10,000 scale service has been created using high resolution cartoset data of 2.5 meter. Base map service 50,000, NIC satellite map service in various resolution scales, NIC terrain map service, which is a very unique, using 20 meter contours of Survey of India, seamlessly available, and NIC street map service in 10,000 scale for entire country. In terms of boundaries, this we update regularly through workflows involving Ministry of Panchayati Raj, involving State Government Revenue Authority in a network at top of base provided by Survey of India. So we have created a workflow to update these boundaries because our NIC runs with number of MIS system where location code directory is required to integrate, say, data from NREGA, drinking water mission, or so many schemes. So this location code directory, which is geospatially enabled, is very important requirement for all projects. So we have most updated district boundaries. What happens, revenue authority in district, whenever new districts gets created or new block get created, they update that information in terms of lookup table on a portal, and from that portal, GIS group gets a service, and we update that boundary geospatially. Now, again, we are now working out a process through which this update boundaries goes to Survey of India and RGI for ground verification with revenue authority. So that loop we are trying to build. So all ACPC boundaries, village boundaries, Gram Panchayat boundaries of around 2,20,000, which we have created by clustering villages. So this framework is available. These are the salient features. We are following OGC standards, risk-based architecture to integrate all kind of services, tile-based map services. So we have large number of point of interest data available, which is built over the period of time with involving various ministries and department. More than, I can say, 50 lakh locations of different kind, like location of all 15 lakh plus schools of the country, location of all banks, including rural banks and cooperative banks created under GIS for financial inclusion part, location of health infrastructure, and this we are creating and building crores of location of assets created under NREGA, Pradhan Mantri Awas Yojana. All those assets is available on GIS platform, including Swachh Bharat Mission, toilets, and all those kind of information is geotagged on at top of Bharat map, base map. All India terrain map seamlessly, just a sample. Various mosaics of satellite imagery in various resolution. These are some of the snapshots and layers available. We have a cloud-based ICT infrastructure. That is very important because this infrastructure is a deployment framework where I get thousands of hits against one map service. Some user wants to access district boundary and consume in his app. So we have to make our cloud infrastructure so robust so that when number of hits or peak comes, it should sustain. So we have built complete cloud-based ICT infrastructure over NICNet, where from single source of truth, map service, without violating any national map policy and security guidelines of the country, can be delivered and consumed in various e-governance applications. This is the deployment architecture where number of web servers, GIS servers, and database servers in NIC data center has been created with proper disaster recovery in, say, Hyderabad and Bhubaneswar. This is schematic how different services, GIS services, are organized for Bharat map using various servers, because all services, layer services, map services, base map services, image services have been deployed on different servers. Say like stack 1, NIC base map service, terrain map service, administrative boundary come from stack 1. Geocoding, reverse geocoding service come from stack 2. So we have, for load balancing, the server architecture, and then they get integrated in various applications. So this is what the framework, how we have organized deployment architecture for ICT to deliver seamlessly at very high performance geospatial services. Like if you see Bharat Maps portal, each of these segment shown in the things are coming from map services, coming from multiple servers, base map service coming from other servers. This is what the schematically I'm trying to show it. Like now, this is the user applications. Now, suppose urban ministry, this is a slide of urban ministry, where all at top you KPIs which are coming for various schemes, smart city, Amrut, and so many things. The data service is coming from those independent platform from different servers and getting matched up with GIS service to generate thematic and analytic scenario at top of same base map. So ultimately, Swachh Bharat Mission Rural portal is different. Pradhan Mantri Awas Yojana portal is different. Smart City portal is different. The data services comes from those portal and get consumed. I am not bringing every data on GIS portal. So machine stocks through APIs and web services and integrated geospatial services delivered. So this is what the model which we are following, and it can be used for agriculture also. We have created a map service portal where I am giving some sort of a developer license of a layer for a developer who wants to consume the map service in his source code in a program. Other day I was talking to Professor Deepak Lal. What I am trying to say is, you need a GIS service team which should have an agriculture engineer, agriculture science person, and also a person with computer science background who can consume your geospatial service in his JavaScript code or .NET code and join your ground survey data with map to create further analysis. So this is what the framework which we have built. The person of computer science does not understand GIS, but he knows how to consume services in his source code. He may not be knowing map projection system, how data is collected. That is different. But if he can consume map service and join his table data or his survey data to create further geoanalytics at top of it, I can multiply the manpower support. I can use my IT infrastructure optimally. That is what the framework NIC is addressing, trying to address. This is the portal where people can apply for map service so that they can get secured map service. And there are 4 steps to be followed. This is the framework which we have created within NIC. Now, I have not made this map service part in public only because data owners has not declared any geospatial data as open data in public. So I give through certain secured procedures those map service which in workflow people can consume. So these are the 4 steps. They have to log in with Government of India email password, select the service, view the map service on fly, access the layer wise metadata information along with information how or SOPs and procedures, so that, and ultimately that map service, when he apply for it, first he will apply for a staging server for development server, and then he will apply for production server when he is going to deploy it. Against the service will be given for a particular IP and URL with a security token. So that only it is giving a specific license key to a specific developer. So that way security of data and requirement of map policy is fulfilled. So this is the way this is the login page. These are list of map service. You can see on the fly available around 35 kind of services are being given there. One can apply service request. He can send. He can see the metadata of the service in terms of its accuracy, scale, all that kind of thing. Then these services are consumed in a multiple applications. So village boundary of NIC is consumed in multiple applications, including those map services are consumed with, say in UP, with what you call Jan Sunwai portal of Chief Minister of UP, where recently they have done the cluster mapping at village on the basis of the grievances received related to COVID-19. Which are the clusters in villages are facing what kind of difficulties due to COVID-19 where. Now, these kind of things, the map service has gone from GIS cloud, workflow data came from Jansunwai portal from field, mashed up, and those mapping scenarios are shown. Now, this is how we are multiplying the usage of geospatial technology in various schemes and programs. These are some of the map service applications: school, CGHS, postal GIS, bank GIS, so many things. These are just a list of various ministries, department using map service for their dashboard applications and other things. Let me tell you one thing. When we see ultimately what happens, even for agriculture, you may find, say GIS application for e-courts not relevant for agriculture, but tomorrow an application come when you need layers from e-court project for maybe related to, say, in agricultural land dispute and some applications. So this is the way we are trying to work out the things. These are some of the snapshots where GIS services are being consumed. Managing CGHS welfare, even mapping of scavengers, child index card mapping for what you call child labor, Mission Antyodaya baseline survey, GIS for Panchayati Raj, soil health card mapping, integrated housing scheme, Pradhan Mantri Awas Yojana Gramin. So these are how. Then for using Bharat Maps data and data from various ministry and department, we have created instance of each state GIS portal, which is available at stategis.nic.in, and people can visualize. You can see for UP, you can see your district Allahabad with all blocks, all villages available there. And in fact, we can collaborate also with, this is the offering for any any research projects and applications. This is agriculture related, some of the applications where GIS based soil health mart. So say soil health card scheme is of Ministry of Agriculture. They are collecting lot of data using mobile app on soil samples, and once the sample goes to lab, all physical, financial, physical and chemical characteristics of soil. That data is coming to us real time as a service, and we are creating thematic scenario and integrating with main portal. So this is how GIS is functioning. Similarly, food processing resource mapping. Now this is done, work which has been done for Ministry of Food Processing, where the requirement of ultimate requirement was to build investment portal, cluster mapping of say mango zone, for example, for say wheat zones of the country, based on the cropping and what you call agriculture census data, which is coming again from real time from different servers. Then after creating those clusters of various agriculture and horticulture products, how to access it, what kind of infrastructure facilities available around, what is the road connectivity, what is the air connectivity, if some investor wants to go, and what is the nearby production and grading facility to test the produce. All those kind of things in integration with Ministry of Agriculture, Ministry of Food Processing, then FASSI, who is provide lot of information, has been put together for food testing laboratories and all that, so that a investor, when he apply under a scheme, he can see this information and see which area has better return on his investment. So this is how we function. NIC is not a primary data generation organization. We don't generate data as such, but we create an environment where data can be integrated and service can be delivered. So ultimately, say we do any application and study of requirement from user and client side, and then look for that requirement, what are the things required from different sources and how it can be integrated. NIC never go to field to collect data first. So this is what we are. Ultimate requirement of this food processing mapping was investment portal for investor. The eSampada portal for inviting schemes, for inviting investor should have access to this information. That is the idea. These are all information related to agriculture crop production, horticulture crop has been integrated here. Access, routing, how to reach a particular cluster. This is what has been connectivity, infrastructure, industrial plots, where the land is available. If he wants to set up certain facility there, what kind of land is available where? This is what cluster vegetable production. Other project which I'm talking about, agriculture marketing network. Now here, location of mandis and with price and arrival information has been integrated. And best scenarios like best prices to farmer in the neighborhood, MSP reported below NSP where is done real time. So most of these mandis feed their data real time. Now I have created a data geospatial network for agriculture market. I will say like that. On the same network, I can overlay agro-met advisory services for farmers, which will maybe coming from IMD real time. In UP, for Rahat portal, what you call for commissioner relief, for flood, lightning, we are integrating data real time from IMD or National Institute of Tropical Meteorology, Pune, so that SMS and alerts can be sent in multilingual way to villages, and that information is being also represented geospatially. So this is what ultimately the Rahat portal is ultimate goal and requirement.
अभी बोल ही रहे हैं.
integrated with Bharat Maps. Then we have worked with for their RVP FPR project for what you call soil mapping, watershed mapping, for detailed soil survey and other things. So this data is also built over the period of time. This is one of the new next slide which I am showing is in again from user side, from central government water board, give clearances, NOCs for abstraction of groundwater, no cap. Now the person who is applying for clearance NOC to central government board, his application comes with certain location information in terms of lat long, or maybe some village and other village name or something like that. This uses geocoding and reverse geocoding service of NIC and integrate with the map. On the same map, or information from groundwater board like aquifer map, groundwater aquifer map, they are what you call dark zones and all those zones information, and they see that location where people are applying, whether they should allow or not allow. So geospatially they take a decision and convey acceptance or rejection of NOC. So this is what how so we started from ultimate goal is NOC to be given. For that certain information will come from field. To make a decision on your map, apart from state, district, village boundaries, you must have aquifer map, you must have a hydrogeomorphological map layer, you must have a dark zone, safe zone, all those kind of information, and then they decide whether it should be done or not. So this is what the decision support system as a workflow enablement is given. Certain work with Punjab Road Organization, where we have given NIC road base map service to field unit to attribute, to value add the road information. They have created themselves on our base map mandi location, mandi boundaries, all these locations, and also they have built road code directory with complete geospatial codification and attribution, defining each segment road, whether it is a state highway, major district road, link road, village road, mandi road, classifying everything through a web-based geospatial editor. And then we have built at top of it MIS integration part, mobile app for maintenance and other things. So this has complete portfolio, and this data is used for agriculture and multiple applications there. Link road editing, village boundaries integrated with mandis, boundaries, planned road, and all those kind of integration of road with their e-Pragati data, Sadak Seva mobile app. These are some of the snapshots of that. Punjab Sadak Seva. I just want go in much detail about, we have also a division and group working on large scale mapping using aerial photography, drone surveys and other things for cities. And we have, it's a, we were the first person to create a 1:1000 scale utility map of Delhi, where all drainage, electrical, sewage, telecom lines have been mapped with ground accuracy of less than 5 centimeters. We have set up complete geodetic network, GCP network, that time in early 90s, first time. And further we have enhanced this for 7 mega cities like Delhi, Bombay, Pune, Delhi, Bombay, Ahmedabad, Chennai, Hyderabad, Kolkata, all these, Bangalore. Some of the projects which we have done is from Slum Rehabilitation Authority, Mumbai, where we have set up the course network also to map the slums and with integration of LiDAR data. E-Dharti Geotour portal for land management in Delhi. A smart city project which is undergoing for Greater Noida Authority. Kavrati Island we are working, and many projects with Delhi Jal Board and many other places. Now, some of the examples which I have already covered in terms of Bharat Maps, there are large number of applications with telecom, with financial inclusion, various schemes, programs has been done using Bharat Map services. This is for GIS or financial inclusion, where all banking infrastructure, because including fair price shops are mapped, because fair price shop is also used as a financial point in the field level. CSC centers, ATMs location. This project was to identify uncovered areas in terms of the banking system. Through this system, all banks of the country, including rural banks, cooperative banks, NABARD, all leading banks are connected. Separate tools and application for data updates on web and mobile with backend validation process has been provided to each one. The data is updated real time. Jan Dhan Darshak mobile app you can download from Google App Store, which is for citizen. Now, this is what end-to-end services. Idea is the data infrastructure for banking system has been built. Tomorrow, if you want to integrate your agriculture related transaction with banking infrastructure, a framework is available. So this is how we are trying to integrate various heterogeneous systems for delivery of services. Telecom, complete optical fiber network mapping is being done for BharatNet to connect villages in Panchayat. This is high level diagram where complete route surveys, as-built drawings has been put together as a system. How this even as-built drawing, route locations, equipment locations, and complete platform is giving for telecom infrastructure mapping. Today, there are many agriculture applications which demands what kind of connectivity and telecom infrastructure is available on field to deliver advisories. So this is what some of the layers may come in here from for any agriculture application from here also. Routing. There is a real-time project monitoring of fiber construction work, where our mobile app is being used by the construction contractors people in a workflow and sending real-time data where trenching is happening, where ducting is happening, where cabling is happening, and workflow it is verified by the supervisors at 2 levels, and then data is committed and the routes information with photograph is come real time. So many project monitoring infrastructure projects are using these kind of systems. This I want to specifically mention here about Swamitva scheme, which have huge implication in coming time in next 5 years in agriculture also. Survey of village and mapping with improved technology in village areas. For drone-based large scale mapping of Abadi areas in revenue state villages. Now, in our villages, the Abadi areas, no land survey has been done since only land survey or cadastral maps are available without any proper georeference for non-Abadi areas. But for Abadi area, people are living there, they cannot do any transaction, they cannot take any loan or mortgage system. So under this scheme, they are trying to create cadastral records of Abadi area. Also, since drone survey is going to be done, drone survey part will cover the what you call non-Abadi area also, because village and panchayat need seamless base map. So this is another work. This map survey part is done by Survey of India, and these are the different roles for large scale mapping I'm talking about. Survey of India is setting up the course network, also to densifying 1:50,000 scale primary geodetic network for the mapping of, say, Abadi area, village areas. So to generate 1:500 scale maps, 1:4,000 scale maps. Flying is done by all Survey of India or ISRO. Data capture through various sensors, various means, MIS integration and service delivery is with NIC. This is just this dashboard is going to be released by NIC soon. These are the different activities under Swamitva scheme is being carried out. Establishment of course network, GCPs, schedule of Gram Sabha, because Gram Sabha is going to be called by state to convince user Chuna marking before drone flying is done. Chuna marking of the property is done so that those boundaries can be captured and drone survey. Now, this is facilitated by state government, revenue authorities, and Panchayat Raj authorities in state. Drone flying and base map preparation, then dispute resolution by state for boundaries by actual owner. Property card creation, they are creating for Abadi area the pattas. Built of GIS database. Now, this GIS database will be available with NIC to be used in various applications. So a lot of value addition work will be required for every application in terms of feature interpretation, feature classification, and remodeling or data re-engineering. So there will be data requirement for Gram Panchayat development plan, land records, for school application, for some other application. Each application data has to be re-engineered. The base information has to be re-engineered and integrated with sectoral geospatial information and MIS information to deliver the services. Like this is just a representation showing the Abadi area in existing Patwaris and Latha map, scanned Mausavi village and Lal Dora areas, Chuna marking. So Abadi area of Sirsi village where one pilot has been done. So this Swamitva scheme is going to have lot of impact in coming time. And we are working with Survey of India for that. And also at the same time with Ministry of Panchayati Raj, we have built a called Gram Manchitra, grammanchitra.gov.in. You can access as a GIS platform from Gram Panchayat Development Planning, GPTP. There, ultimately, this drone survey data will be integrated. Currently, the platform integrates data up to 10,000 scale, which is available on Bharat Maps. On the same platform, with respect to village panchayat boundaries, data will come from NRSC on water resources, on soil resources, and so many things. And now Ministry of Panchayati Raj has engaged more than 20 institutes of school planning and architecture to build master plan of cluster of panchayats. Like you have a master plan of cities, similarly master plans of cluster of panchayats where land use classification can be designed, some model to build housing, smart housing for rural population, so that on choice people may be shifted from Abadi area to those housing places where smart transport, smart services along the highways, shopping complex and all are available, and vacant land done during the process can be utilized for other things like setting up the solar farms. So and during this process they want to do the delimitation of panchayat so that panchayat becomes a viable economical unit. So this is what the plans of Ministry of Panchayati Raj, and with them we are working this creating a complete geospatial platform for GPTP with complete, and already on this platform data from say school, from school GIS, bank from financial inclusion, scheme data from NREGA, drinking water data from drinking water schemes has been integrated and intersected with respect to panchayat boundaries. So a resource envelope creation with respect to panchayat boundary as prescribed in 15th Finance Commission report. Okay, you have to build a economically viable resource envelope for each panchayat. That concept has been built in this portal. So we are evolving this, and definitely when I go for panchayat and I have to create a rural spatial planning model, I need a model for say agriculture resource plan or irrigation resource plan, water resource plan. How those kind of concepts I can integrate in a manner so that panchayat functionaries can use it for implementation purpose. So basically demystifying the whole rural spatial planning process, that is a big challenge where academician and research institutes can play a major role. These are some of the snapshots of existing portal. This is the resource envelope where various schemes, you see the bottom, the data from various schemes are also integrated. Proximity analysis, query, buffer, multiple buffer tools, various schemes, socio-economic caste census data is integrated, mission Antyodaya analysis, gap analysis done, mission Antyodaya report. All this is with respect to panchayat boundaries. Elevation profile of a panchayat, real time you can generate using 20-meter contour of Survey of India. Swipe tools, metadata, measurement tools, base map services. So I have talked about these three important URLs. Include fourth one is a grammanchitra.gov.in. You can see at your end anytime. Now, I just want to talk about certain platforms. Today, they may not be having a GIS into it, but as things are moving, geospatial location components are going to get added into it. And these platforms may have in future some bearing on agriculture delivery systems. One is what you call e-way bill. This is a huge platform where if you talk about supply chain, movement of trucks, the what you call jise kehte hain chungi, octroi, all this abolition of check post, encouraging the self-reporting, reduction in transport time, science, time saving and effective compliance, all these things. This is one of the platform which has increased the tax collection and it can be a part of any supply chain system. PFMS is a very largely used public finance management system. This system today is being integrated in all application where direct benefit transfer has to be given. This has at the back end integration with UPI, all payment gateways of banks, Paytm and other things. So every delivery of benefits to beneficiaries, whether they are farmers, whether they are unorganized workers, whether anybody or school teachers, any benefit, Ujjwala Yojana benefits are going through PFMS system. Even government salaries and other things are through PFMS. Payment to contractors or service providers engaged by government is through PFMS. So PFMS is a platform, huge platform, and during this COVID time, it has been used to the maximum. Around 60,000 crore plus payment through PFMS has been done as a direct benefit transfer. PM Kisan portal, this is very much talked about PM Kisan portal, where every quarter 2,000 rupees has been given for the welfare of the farmer. So again, I say that whether it's a crop insurance, lot of data model, risk assessment of vulnerability. Now, how those data models can be integrated with crop insurance scheme, and crop insurance scheme run by Ministry of Agriculture has its own IT platform. So until unless research models to decide the insurance cover based on the resource condition of vulnerability assessment of particular area it does not become part of workflow, the benefit will not reach to the grassroots level. So this is what I am trying to convey. Direct benefit transfer in fertilizers, e-urvarak, complete science supply chain of is mapped here. We plan to integrate GIS here. So these are some of these applications, platforms application. PDS system. So all these platform systems where now geospatial is being integrated. Geolocation of all ration shops is collected and mapped. E-courts from Supreme Court to district courts are put together as a part of the network and service delivery system. E-transport, complete system. If you see pollution check, fast tag, integration with courts, with external applications integration, dealers integration, automobile manufacturer integration, banks integration, insurance companies integration, transporters integration, citizens integration. So on a single platform, all these services are available. Tomorrow, any one of the services, if agriculture supply chain, if you have to manage agriculture supply chain, some of the services, data service may come from this platform, depending upon the requirement. Vehicle location and tracking system through GPS and IoT devices. So these are the things which has direct linkages with supply chain. This is what I am trying to say. NIC is also managing open government data platform, data.gov.in. And this is what, as a part of implementation of National Data Sharing and Access Policy, NDSAP 2012, launched by Department of Science Technology. They have asked every ministry department to declare their chief data officer. They have asked each department to have a positive list or negative list of the data. If data is in positive list, it will be pushed on data.gov.in so that anybody can download, use the service and APIs to develop his own application. If they are negative list, they will deal with the policy, security, and all that kind of thing. So this platform is available, and thousands of data sets, lakhs of data sets are available, which anybody can consume those resources and develop their applications. And our open data team conducts hackathons or challenges every year. So those things are also done. At the last, these are some of the awards which we have received. And finally, I conclude saying that for agriculture, you have to enable digital transformation covering end-to-end workflows and processes, integrating various data models, enable using GIS, integrate various digital technologies from data capture to service delivery, collaborate with state, district departments and research institute for have effective and efficient delivery systems. Thank you.
Thank you, sir, for your presentation.
Thank you very much.
Sir, it was an excellent presentation. Thank you so much, sir. Very informative.
We received a lot of information and will be in touch to get more details in future, sir. Now I would like to welcome Dr. Daniel Zakaria, Agriculture Water Management Specialist, the Department of Land, Air and Water Resources from UC Davis, USA. Thank you, Dr. Zakaria, for this webinar. Now,
thank you very
switching
much.
mic to you.
All right, and I can share my screen, right?
Yes, you should be able to share. Let's see. Yeah.
All right. Let me see. Is it visible in presentation mode?
Yes, looks good.
All right. So I'll scale down the level now because I will speak about, I'll give an overview on applied research effort that we are conducting here at the University of California to improve agricultural water management. And I'm an agricultural water management specialist in cooperative extension, and that means basically that most of the work that cooperative extension do is directly with growers association, state agencies. So we basically are academic, but with the specific role of connecting the production community with the regulatory community and with the science. And so we basically do apply research, and we bring the research results to growers and state agencies in order to make improvement in management practices, especially in my case, I work a lot with commodity boards, and so with a production group for different crops. Here's a brief outline. I'm going to give you a little bit of background information on California agriculture and water. So we'll bring everybody to the same level, and we'll touch upon some long-term trends and some water-related challenges that we are facing and we're going to be facing in the near future. And then I'm going to describe a couple of projects where I led a group of scientists and colleagues for improving the agricultural water management of pistachio production. In California, pistachio is a very important crop and is expanding. But before doing that, I'll provide some example of integration between geospatial and ground-based technology that we normally use here in California. And as I mentioned, I'll talk about this project that we just almost finished. We are wrapping up the results, and this is related to updating information on water use, evapotranspiration and crop efficient of pistachio orchard grown in the San Joaquin Valley of California with microirrigation on non-saline and increasingly saline soils. So my presentation will be very applied and will show the somehow unique profile that we have as a cooperative extension researcher in California. So before entering the presentation, I'd like to give you some information about the University of California Cooperative Extension. This is a network of researchers and educators that are working together to solve problems. It's called an engine for problem solving, and we solve problems related to agriculture, natural resources management, food security, and nutrition for the people of California. The University of California Cooperative Extension consists of 130 cooperative extension specialists like me. We have statewide responsibility. That means that we can work in every part of the state and also in the boundary states. There are 57 county offices of the University of California, so almost one per each of the different counties in California. And here's where basically there is the interface between the university research and science-based activities and the production, agriculture, and the life of normal people. In total, there are 200 locally based cooperative extension farm advisor and specialists. That means that some of us are based on the different campuses, and some of us are based at the county level. But also we got 9 research and extension centers throughout California where there are farm advisor and specialists that work together in order to develop and execute research projects and also outreach the results to the stakeholders. Now, California agriculture, here's a few information about California agriculture. It consists of 77,000 farms. Those information were taken from the United States Department of Agriculture and specifically from California Department of Food and Agriculture, and are related to 2018, basically to the crop season 2017. So all in all, California agriculture generates about $50 billion industry. It's a huge industry, but as you can see, it counts very little, less than 2% on the gross domestic product. So the gross domestic product of California is 3.01 trillion US dollars. And so this amount, the $50 billion, counts for less than 2% on the total income, because there are other industries that generate much, much more income. We got, in terms of acreage, we got almost 10 million hectare of agricultural land, out of which 5.7 million are rain-fed, and those are pasture and rangeland, and 3.8 million are irrigated cropland. And out of this 3.8, 2.5 are basically annual crop, and 1.3 are permanent crops, so orchards and vineyards. In total, in California, there are more than 400 crops are grown. So it's a huge industry. It's very diversified from north to south. And here's a few records. California is the #1 food and agriculture producer in the nation, in the United States, and has been so for more than 50 years. And more than 50% of the US fruits and nuts and vegetable is produced in California. So the state of California produces more than half of the fruit and nuts and vegetable that is somehow used in the whole nation. And also, California is the #1 state for dairy production. Here is the cash income, the California agriculture income divided by commodities. Again, this data are related to the crop season 2017. As you can see, fruit and nut crops are basically in a #1 commodity and generate almost 40% of the total income. And then you see livestock, vegetable crop, field crop, floriculture, and all the other crop. All in all, as you can see, the total cash income in 2018 has been basically $50 billion. It's increasing year by year. So there's a lot of room for expansion and intensification of irrigated agriculture in California. Here is a map of the state with the different production area identified in different colors. As you can see, Intermountain, Sacramento Valley, San Joaquin Valley in yellow, and the Central Coast. Those are the highly productive agricultural area. It's called the fruit basket of the world. So most of the agricultural production comes in this yellow highlighted area, and this is called the San Joaquin Valley, and is also has been named several years ago as a fruit basket of the world. And alone, the San Joaquin Valley generates basically 60% of the total agricultural income of California. And in terms of water use, the whole state requires a huge amount of water to sustain the agricultural production. And this is being quantified in about 20,000, it's actually 26.3 million cubic meter of water per year. And out of the total beneficial water use, which is 99 billion cubic meter per year, as you can see here in this pie chart, most of the water in California is used to maintain a functional environment, so for environmental purposes, because a healthy environment has a value, and this value reflects in the well-being of people, and so it's considered beneficial use. 41% is on average used by irrigated agriculture, and about 10% is used by the urban sector, which consists of the municipal and industrial sector. As you can see, the two main water users in California are the environment, #1, and agriculture is the #2. So there is a big pressure on make the use of water more efficient. So some water can be free to improve the environmental condition and also to accommodate the urban expansion. And I'll show you, this is becoming really a challenge. In terms of water demand and water supply, most of the water supply is generated in the northern part of the state. Here in the Sierra Nevada mountain is a snowpack. And of course, it's generated as precipitation, let's say rain and snow during the wet season. So during the winter months, so December, January, and February. then most of the water demand occurs in the central and southern part of the state, and of course occurs during spring and summer. And so this basically means that in California, we have to move water in space and time. And this happens in this with a kind of sophisticated system. So most of the water is stored in the mountain as a snowpack, and then during the late winter and spring, the snowpack melts and generates runoff. Runoff is accumulated in all the storage reservoir, and then is recirculated through the state with a capillary network of canal conduits, and also through the aquifer. What are the long-term trends and actually the water-related implication? I'll call them challenges, because you'll see what we're facing here. So first of all is that the population is growing at a very fast rate. And this is the point where we are now. We are about 40 million people. But if the projection stay constant as the past has shown, we're gonna increase much more in the next 10 years. So we're gonna almost reach 50 million people. And when population is increasing, the first implication is there's more demand for food to feed a growing population. And also this food has to be healthy and somehow sustainable in terms of production. All right. But at the same time, the population growth means that a lot of the land is then subtracted from agriculture, and it becomes urban sprawl. So urban expansion is subtracting a lot of land from the agriculture production. Here's some numbers. During the period between 1984 and 2010, so 15 years more or less, almost 450,000 hectares of farmland has been lost because of the urban development. And most of this farm land that was lost in the San Joaquin Valley, so in the area that is the highest, actually the most productive for agricultural goods. And here's the map. As you can see, the urban sprawl here that is forecasted for the future is indicated in light green and dark green. And as you can see here, if the population keeps increasing, we're gonna have less. We're gonna have to produce more on less land. And of course, when the urban population increases, the urban development increase, and they take the best land, and in most of the case, the most fertile land. So this has an implication. So we need to increase the production in less land, and also land that is less fertile. And this land that is less fertile basically requires more inputs, and the inputs are basically fertilizer, nutrient, and water. So this is basically a very limiting situation, because on the one side we have to produce more, but the other side we have to produce more efficiently. And I think there's some room for improvement, but at a certain point, we're gonna hit the wall. And in terms of sustainability, this has a lot of implication. California agriculture is highly efficient, but I would say that is not sustainable so far. And so we have to make an effort to make it sustainable and not compromise the natural resources for the future generation. Something is happening in the climatic pattern. And so Dr. Tapan Pathak will talk tomorrow about the climate change impact. So I will not touch too much on this. But what I wanted to show you here is in blue, you'll see the precipitation, the 70-year average of precipitation for the northern part of California, where most of the water for agriculture is generated. And this curves in red shows the precipitation that we had in 2014 or 15 in the hydrologic year 2014 and 15, where we had drought. And the following year, 2016 and 17, we were not in drought, but we were in a very wet year. So there's a big fluctuation from one year to the other. So California is really characterized by an alternation of drought and flood. And this fluctuation are becoming wider and wider and are becoming also more frequent. So a drought is happening every 3, 4, 5 years, but it's very unpredictable. So this unreliability in the natural supply of water is also creating some problem in terms of storage and in terms of use of the stored water and use of the aquifer. Now, the third trend that we're noticing in California is that the intensive agriculture is relocating. It used to be spread throughout the state, but now is concentrating in 3 areas here in the Bay Delta area, which is an area around the city of San Francisco Bay, and then the Central Valley, which is this part, and then basically the desert. So this is the Imperial Valley that gets water from the Colorado River Basin. So the cropping pattern are intensifying. So we're seeing a lot of intensification in terms of growers are shifting from annual crops, from field crops to perennial crops, mainly fruits and fruit and nut orchard and vineyard. And we're seeing the growers are planting with higher densities of plants, and this requires more input per hectare. And there's also a shift from different irrigation methods like surface irrigation and sprinkler irrigation to micro irrigations, basically drip and micro sprinkler. Now, as a result of all these changes, the productivity, the economic productivity of water over the years, over the last few years, has increased by almost 35%. But this economic increase of the productivity of water comes with a cost, and the cost is basically borne by the environment. So there's for sure higher economic productivity, but this is at the cost of sustainability, because again, this economic performance indicator does not consider the value of the environment and the cost and the environmental influence of what is happening in California, right? So there's another trend, basically. I think there's a wide misconception about, you know, the water conservation and water saving, and the state is supporting and encouraging a shift towards micro irrigation, again, for saving and water conservation, and providing incentive to growers. But this doesn't come with a reduction in water use, because farmers basically follow the push by the government and shift from field crops to permanent crops. But at the same time, they expand. They think they're saving water, and so they think, okay, all that water that I'm saving, I can cultivate, I can crop more land. And so this basically has shown that the improvement of efficiency of water use has not brought any reduction in the total amount of water that is used at the state level. So the amount of water that is used is basically increasing as a result of the higher efficiency in the irrigation method. Here is the results of a survey that the Department of Water Resources and University of California conduct every 5 years. And you can see here in the x-axis the time, and here the percentage of irrigated area for the different type of system. here, gravity system in black has been decreasing constantly over the years. The difference has been picked up by micro irrigation over the years, and sprinkler irrigation and other methods have remained pretty much constant. So there's a clear trend in intensification of higher efficiency method, but at the same time, this comes also with a conversion from field crops. You see here the field crops decreasing over the years, and vineyards and fruit orchards are increasing over the years. So this is basically showing you the higher efficiency water application, but at the same time, higher demanding crop and more steady income, and at the same time, hardening of water demand. So when you have a drought, the permanent crops are considered an investment, so you have to somehow irrigate them. Otherwise, you will lose the investment. And so basically, there's no much flexibility anymore because all this investment need to be somehow irrigated constantly. And so during the drought, there's a lot of problem. All right, so but this agriculture intensification means I think I lost the audio. So, but anyway, I was saying that this increase in efficiency and in agriculture intensification means that we need the the irrigation management need to be more accurate and precise. In order to do that, basically there's a rationale for optimal irrigation scheduling in California, and so this is the rule is to irrigate according to the crop consumptive use, or basically ET of evapotranspiration of the crop. And this is referred to well water conditions, so where the evapotranspiration of the crop can be calculated as a product of reference evapotranspiration. In this case, for California, reference evapotranspiration is grass multiplied by crop coefficient. Now, the state has done a lot of, as you can see here, this is an indication of crop evapotranspiration, reference CT, and crop coefficient. All right. So the state has done a lot of progress in making reference CT data available throughout the state, and has created the CIMIS network. It's called California Irrigation Management Information System. It's a network of, now there are 152 automated weather stations that provide for free to all growers and all users daily or hourly information on reference CT. And I'll show you also an example of that. But at the same time, there's a new product on the available, again for free, and made available by the National Weather Service. Is called FRET, or Forecast ET. So basically, there's a prediction of 7 days and 10 days, 1 day, 7 days and 10 days of the reference evapotranspiration. So irrigation scheduling can be predictive, and so we can schedule irrigation for the following season, the next season, with this new product. The problem is that all the crop coefficient information that we have were developed in the past 20 years or 30 years or more, and we don't know whether they're still basically valid in the current condition with this alternation of drought in flood that we have. Here's an example of the FRET. As you can see, I think I downloaded this forecast today because I was doing an irrigation schedule for one of our citrus growers. And so you can see here the Friday today, Saturday is tomorrow, up to 7 days, we get a sense of how much reference ET we're going to have in the different location of California. Now, if we have good information about crop coefficient, then we can combine these two information and provide a number of hours of pump operation or irrigation system operation to the different growers. And this can be done by hand, or can be done with Internet of Things, or can be done automating the process. And some of the growers have put together some automation also of the irrigation scheduling development. All right. So here is the map of CIMMYS developed in 2005. At that time, CIMMYS, the California Irrigation Management Information System, had about 60 weather stations throughout the state. And so people in the state with the UC Davis, they did an effort and they defined reference ET zone. Actually, there are 18 reference ET zone. In 2017, the Department of Water Resources have now 152 stations, and so has thought about refining the map of reference ET zone. And here is the map basically that is being finalized. There are a little bit more reference ET zone, but because now we have more stations and we have the possibility to interpolate better the reference ET data. But the state has also developed another product that is called Spatial CIMMYS. And so if your farm is located in an area that is not close by a reference ET station, then by interpolation, you can download the data for free. Now, this is an example of integration of spatial technology in ground data, because this map is developed every day and is made available every day thanks to the geostationary satellite that is called GOES. It provides a daily, hourly and daily value of net radiation, and with the ground measurement of the parameter at the meteorological station of CIMMYS, it's possible to calculate reference ET. So this is a practical example of integration of ground data with remote sensing and satellite remote sensing data. And it's a pretty accurate product. And so if you're in a remote zone that is somehow far away from a CIMMYS station, you can get online, click in the point that relates to your location and get the reference ET information. All right. Now, in terms of crop coefficient, those crop coefficient information for the different crops were developed during the 70s, the 80s, and the 90s. And those were developed with methods that were either very laborious or indirect methods. So what I mean is either using lysimeters or using a soil moisture depletion and calculating the soil water budget, or a neutron probe, or sometimes were developed by educated guess by experts. But anyway, the crops at that time, during the 70s and 80s, were very different from what we have now. The irrigation methods were infrequent, so they were like surface irrigation or sprinkler irrigation with a frequency of 2 weeks to 1 week. Now, all the crops are mostly micro irrigated, and so there's also genetic improvement done over the years, and this means that now the crop that we have, the variety and the rootstock, have much higher potential, much higher production. And so the question is, can we still use a crop coefficient that were developed like 40 years ago, 50 and 60 years ago, for cropping system totally different, for scheduling irrigation now? And the answer is basically no. We have to update all the information that we have according to the new varieties and the new irrigation system, the new irrigation frequency, and so forth. So there are other also crops that in the past were not very spread and not very common, like citrus. Now citrus is planted citrus orchards are planted with different variety, especially mandarins, with different planting density, with different canopy management, a row orientation. And so having one crop coefficient for all kinds of citrus is basically very inaccurate. Pistachio was planted 30, 40 years ago in California, but now is expanding on saline soil and saline sodic soils. And so we don't have any information on crop coefficient of pistachio on those soils. Wine grapes is now being planted on sloping areas with different aspect and different trellis. And so for all these crops, they are so now diversified, we don't have sufficient and accurate information on crop coefficient. So there's a clear need of for updating the ET and crop coefficient information, both at the farm level and at the watershed, water district, and state level for different purposes. So I listed here the different application of having reliable information of ET and crop coefficient of the different crops, but I'm not going to go in detail for the sake of time. So there are also a lot of interest in estimating the crop evapotranspiration and crop coefficient by remote sensing. And as you can see here, I put together a table with different methods and the model and different name of the model that use different methods. So for instance, vegetation index based remote sensing model, we got at least 2 or 3 that are being tested in California. Then we have surface energy balance method with CBOL, metrics, SEBS, and other more sophisticated method with other models. So there's a plethora of models out there, and this is just an example of one application of a model that is called TopSIMS, and they use this vegetation index versus crop coefficient relationship in order to map evapotranspiration over large areas. Here is a map of evapotranspiration over the different years of the same date that is obtained with another model that is called metric. And all this model requires a lot of assumption and a lot of parameters because they're models. And so, and all these parameters requires a lot of calibration. Just want to give you an example of how this model performed in California in an area that is called the San Francisco Bay Delta. 2-3 years ago, the University of California and the state of California engaged in a large project to map evapotranspiration with different remote sensing based model and with ground-based data. Here's a map of the cropping pattern, the land use of the area of the Delta. And as you can see here in different color, the different crops, alfalfa, almonds, citrus, corn, and all the different crops. And here is what you get for the different crops with the different models. So there are 5 different models, and each and every model gave different results for each and every crop with a lot of variability across the different model and across the same crop. And so basically, which one is right? And this was done without calibration. So all the research groups were asked to run their model without any calibration to see whether there was some kind of proximity of the results. And of course, there was no proximity whatsoever. Here is the total amount of water estimated in terms of evapotranspiration for the total area of the Delta with different models, the calcimator, DTOT, DISALEXIS, ITRC metric, SIMS, UC Davis metric, and Priestley-Taylor. And as you can see, each and every model gave a very different results without calibration. When calibration was done through some ground measurement, the different model, somehow the variability among the results of the different model was reduced, but still you see there, quite the results of the different model are quite different. In this example, I pointed out this example to say that we at the University of California believe a lot in field activities and field ground truthing and ground data collection. And so we never rely totally on a remote sensing model, but we want to make sure that the information we provide to growers or to the state agencies are accurate and solid enough, because otherwise they can be misleading and they can be leading people also to court and to other type of problem. So in the last 5 years, actually 6 years, I joined UC Davis in 2013. I engaged in a variety of research study that aim at improving irrigation management of permanent crops. Some of the project related to wine grapes on slope. I did this together with, in collaboration with other colleagues, both in California and in Chile. Pistachio is one of our largest effort. The project on pistachio aimed at updating information on ET and crop coefficient of pistachio orchard grown on increasingly saline soil. And also we are in the phase of concluding a project on citrus ET and crop coefficient. And citrus is being we are collecting data from the ground and from drones and airborne remote sensing in order to come up with a better, more accurate crop coefficient for mandarin and navel oranges with different planting densities and different canopy orientation. I'm going to focus only on the case of pistachio because it's where we have conducted now 5 years of data collection, out of which 4 years are good data. And so because evapotranspiration is an energy dependent project, we apply the basically the energy balance, the residual of energy balance models. So we calculate how much energy is being used to evapotranspire water from a crop surface by measuring some of the parameters like net radiation, sensible heat flux, in ground heat flux and sensible heat flux. So, and we calculate the evapotranspiration, which is this latent heat flux, by difference. So we don't measure the latent heat flux, but we calculate the latent heat flux, or ET, of the crop from a difference between net radiation, ground heat flux, and sensible heat flux. And of course, we the surface energy balance parameter can be measured all from the ground with different type of a measurement sensor and equipment. And this is an example of our ET flux station in one of the pistachio study orchard. Here's another station being installed in grapes, in wine grapes. Or these parameters can be also estimated with satellite remote sensing or airborne remote sensing or drone. Or, you know, we can somehow follow a combination of the two methods and estimate some of the parameter with remote sensing and some of the parameter from the ground. And so for the ground measurement, we use basically this simplified equation of the residual of energy balance, and we measure net radiation with the net radiometer. We measure sensible heat flux with heat flux plate and soil temperature probe, and we measure the sensible heat flux on the ground with two methods. One with eddy covariance technique that requires a very expensive three-dimensional sonic anemometer. And also we use the simple thermocouple, and we apply a different method that is called the surface renewal, that was developed here at UC Davis, was patented a few years ago, and is being tested for many, many years in many crops now. So when we do research project, we have parallel measurement of sensible heat flux, so we can calibrate one method versus the other and obtain more reliable information. Again, in some of the projects that I showed you, especially in pistachio and citrus and grapes, we also are testing a hybrid method that combines the use of ground measurement and remote sensing estimates. For instance, we are measuring net radiation from the ground, but also measuring with drones or airborne. And this is an example of what we can get from a high resolution airborne remote sensing platform. And but also from the remote sensing technique, we can estimate the canopy cover. We can somehow estimate the canopy temperature and the soil temperature and come up with some vegetation indices. And normally we measure the other parameter, which is most important, which is the sensible heat flux from the ground, because sensible heat flux is a little bit estimating the sensible heat flux from the remote sensing or proximal sensing might be pretty inaccurate, especially in micro irrigated crops where you don't have the total coverage of by the canopy of the soil. So we call it a partial coverage crop or heterogeneous stand. So the sensible heat flux in this case is when is estimated from remote sensing is somehow inaccurate. So in this idea, the hybrid model, we combine remote sensing estimate of net radiation and ground measurement of sensible heat flux, and we combine them to see whether we can obtain better results than only estimating everything with remote sensing, or better results than estimating or measuring everything with ground measurement. Okay, so pistachio, we'll move to, I'll show you a little bit of the results that we got on pistachio. This is data from statistic from the USDA, so United States Department of Agriculture, that shows pistachio as a crop number 5 in California in terms of acreage, number 5 in terms of production, and number 4 in terms of value generated among all the most important and water demanding permanent crops. In 2018, the total area of pistachio was around 150,000 acres in California. 110,000 acres are bearing, so they're already in production, and 50,000 are coming to production. And so there's an increase in production that will come up over the next few years. Total production was almost 1 million pounds, so like 500,000 kilos, so 500 tons. An economic value generated by pistachio in California in 2018 was $2.6 billion. So it's a big crop, and most of this crop acreage is in the San Joaquin Valley, in the southern part of the San Joaquin Valley. And in the last 15 years, pistachio acreage expanded very broadly on marginal soils, and that means saline and saline sodic soils, because it's very tolerant to stress and very resilient to stress. So when water comes back on these soils, the tree goes back to production pretty fast. This is what we call resiliency. All right, but you know, all this area where pistachio is grown, it basically correspond to the area in California where there's a lot of groundwater depletion, because all the pistachio is micro-irrigated. And so micro-irrigation requires water every day, a water supply every day, and most of the water district in California deliver water almost every 7 days or every 10 days. And so there's a mismatch between the surface water supply and the water demand at the farm level. So growers, what they do, they drill well, and they take water from the groundwater, because the aquifer is considered somehow an on-demand type of water delivery system. And so over the years, especially because of the drought, the aquifer in California has been depleting and degrading in quality. And now, you know, this map shows the groundwater level decrease in the last 6 years, and there's area where the groundwater level has decreased by 20 meter or 25 meters. So all these dots in red is basically where pistachio is planted. And so all this area will face a reduction in groundwater supply over the next 20 years because the state of California has issued a new groundwater regulation that reduced the groundwater withdrawal in some areas by 30% or by half. And so there's really a problem here because the crop is expanding in area where water is limited. And so we don't have enough information on how much water is needed by micro-irrigated pistachio on non-saline soil and on increasingly saline soil. So in 2015, we started a research project and to measure pistachio evapotranspiration and to determine the crop coefficient of orchard grown on non-saline and increasingly salt-affected soil. The objectives were to update information on water use on well water micro-irrigated pistachio, and so also quantify the effect of soil salinity on the amount of water evapotranspired. And here's our hypothesis. So when soil is saline, there's a lower osmotic potential in the soil, and this reduces the ability of the plant to extract and use water. And of course, this comes with the reduction in actual evapotranspiration. And at the same time, this less water use leads to a reduced yield. And so there's basically an osmotic effect, but also because there's a reduction in yield and reduction in canopy growth, there's also an energetic effect because the trees on saline soil have a smaller canopy, so they intercept less radiation. And because ET is an energy dependent process, intercepting less radiation means that the crop is transpiring less water. Here's an example of the non-saline orchard. You can see EC of the soil is around 2 decisiemens per meter. FPAR is basically a measurement of the photosynthetic active radiation intercepted by the canopy. FPAR is basically a proxy of canopy cover. And here is our increasingly saline orchard. So S1, so low saline, S2 is medium saline, S3 is high saline. As you can see from the picture, the tree basically becomes smaller and smaller as long as the salinity level increases. So see, the canopy cover here is 55%, in medium saline 45% and 35%. So basically, as the salinity increases, the tree develops much less. The study site that we have are in Fresno and Kings County. Here is a map with the study site. So we have 1 non-saline orchard here and 2 saline orchard here, and then a 3rd orchard on the actually on the western side of the valley. Here in these 2 orchards, we were able to collect 4 years of data from the ground, and here 2 years of data. All right. And so basically here we got 1 biennial cycle and here 2 biennial cycle. With this, I mean pistachio as an alternate bearing habit. So has a 1 year on of production and 1 year off. And so as a pretty unique in this behavior. And so we need to basically collect data on 2 years or multiples of 2 years. Here is just a picture of the orchard. And here you can see our ground flux station. Those are ET measurement towers. And here the pistachio with salinity, you see a lot of spatial variability. And so initially we installed 6 ET stations, and then we reduced to the number of 3. This is low saline, medium saline, high saline area of the same orchard. And here is what we get from airborne remote sensing flights. And this is an example of an NNTVI map taken in 2015, a certain day, and then also we flew with airborne and thermal camera in order to determine also the canopy temperature. Remember, when we did this survey, we were also on the ground taking stem water potential and taking measurement of the crop canopy. The activities that we conducted over the years, so we measure ET in all this orchard above the canopy, but we also measure ET below the canopy in order to quantify the soil evaporation and the incidence of the soil evaporation above on the total ET. And we also try to capture the difference between the orchard and within the orchard. And we also measure the light interception with what we call the mu light bar. This is basically a little tractor that goes through the orchard and measure the amount of light that filters through the canopy. And so by difference with the incoming light, we can get a sense of the light interception. And so we kept scanning this orchard over the course of the season in order to understand the canopy light interception over the crop of the season. We also measure the plant water status with midday stem water potential, canopy temperature, and dendrometers. These are a few pictures. We measure the soil moisture because we want to make sure that what we measure here, the ET of the orchard that we're measuring is related to well water condition. And we also conducted electromagnetic soil survey in order to understand the spatial variability of the soil feature and the soil water salinity. The idea was to link the soil water salinity spatial variability with the spatial variability of the crop canopy and light interception, and then determine the relationship with the evapotranspiration and crop coefficient. At the end of the season, we also collected the nut yield and quality, nut quality data over the course. Here's the results that we obtained: non-saline, blue line, low saline, medium saline, and high saline. As you can see, there's a sharp separation between the evapotranspiration of this orchard. All this orchard are well watered, but some of this orchard are on saline condition, but they're still well watered. So there's a clear reduction in evapotranspiration as long as the salinity increases. And the ET reduction that we got is 11% for the medium, sorry, the low saline. I cannot read because I have, but you can see the percentage of ET reduction for the different levels of salinity. Also, we compare the crop coefficient that we measured, we obtained from the measurement of ET with the FAO crop coefficient. This study presented in the FAO irrigation and drainage paper number 66 was conducted in around 2002 in California on a sprinkler irrigated orchard. And so here you got the value of the FAO crop coefficient and the value of our study for the non-saline. And here is a graph. Here, in blue, you got the FAO crop coefficient values. And here what we got from our study. As you can see, there's a clear difference. Those are non-saline, the blue lines are non-saline. And so the plant is using much less than was measured before. And I can explain the reason why. And so there's a almost 30% difference between the water use of the non-saline orchard with respect to the crop coefficient provided by FAO. And when the orchard became saline, the level of water use decreases as the salinity increases. And so basically salt affected orchard pretty lower crop coefficient than the non-saline. But still in California, growers utilize this value of crop coefficient because we haven't published the result yet. And they utilize this value of the crop coefficient, so they apply much more water than what is needed, and they basically create additional problem. So we also quantify the decrease in tree performance for the non-saline versus low salinity, medium and high salinity, and I put everything here in the table. As you can see, we consider in terms of performance the canopy cover, the actual evapotranspiration, and the yield, and we basically measure how much reduction we should expect of each and every of this parameter. And when we combine these three parameters in a single reduction coefficient, here's the percentage of reduction that we got. So the low salinity has 19% lower performance than the non-saline. The medium salinity has a 30% of reduction in terms of the tree performance with respect to the non-saline, and the higher salinity orchard have almost 50% tree performance reduction. Now, everything can be scaled up now because we have obtained very solid results, and these results are being consistent over the year. Here's a map from the satellite of all the pistachio acreage in California. You can see pistachio in this light green. When we mask all the other crop, here's the pistachio acreage spread out. With the result that we obtain, we can scale everything up, and we can basically calculate the amount of water demand for the whole area where pistachio is planted for the different time step for the different years. And so things can be scaled up with the use of remote sensing and GIS. I want to show you a last slide where we run a model, a remote sensing model on our pistachio orchard. This is basically metric. And here's the result that we obtain. So in this graph, you will see metric on the ET estimated with remote sensing model metric. And here in this in the x-axis, you'll see what we measure from the ground. And the graph on the left is for the day of satellite overpass, and the graph on the right is for days of satellite non-overpass. And so you can see the variability that we get from the metric satellite remote sensing estimate is pretty high. So it's plus and minus with respect to one-to-one line. And so, and here is the statistic that we obtained from this evaluation. So for the control, there's a 15% difference. For the medium salinity, there's almost 45% difference in estimate between our ground measurement and the remote sensing estimate. And then you can see the other statistic for the high salinity and in total as an average. So my perception is I used to be a modeler and I used to be a remote sensing and a GIS person. But I think we really need to do a lot of ground truthing, because if we rely on only remote sensing estimate and GIS and all this technology, we might be very way off, like plus and minus 45%. And as the level of stress increases because of the salinity, so it shows that the remote sensing model metric cannot really capture with a good level of accuracy what is going on the field. So I stopped here. I apologize if I overflew with the time. And this is a team effort that I showed. And I have to acknowledge a lot of people who are collaborating with me, and also the growers, collaborators, and the funding agency that allowed this different project to happen. Thank you very much. And I'll be happy to entertain any question.
Thank you, Dr. Daniel. Your presentation topic, an overview on applied research effort to improve agriculture, water management in California, was very informative. We are shorting lack of time, so going with our new next speaker, Dr. S.P. Agrawal from Dehradun. Dr. Agrawal is a group leader and water group head of water resource at Indian Institute of Remote Sensing, ISRO Dehradun. He is also a alumnus for our college, so it is a great A pleasure to invite Dr. Agrawal. He has more than 30 years of experience in the field of remote sensing and GIS applications in water resource management. The title of his talk is Remote Sensing and GIS Applications for Water Resource Management. So please welcome Dr. Agrawal.
Yeah, thank you, Dr. Assis. Can I share my screen?
Yes, sure, sir.
I hope my screen is okay.
Yes, sir. Perfectly all right. Please go ahead, sir.
Fine. So I should start now. So good afternoon. I especially thank Dr. Deepak and Dr. Assis and John Wesley for inviting me to deliver a talk on remote sensing in GIS application in water resource management. Indeed, it is my privilege and honor to present before you because I am the alumnus of SHUATS, formerly known as Allahabad Agriculture Institute. I did my BTech from 1984 to 88. And that time, Dr. Lawrence, who is currently Pro Vice Chancellor, was my senior. So I can see my seniors also. Fine. So let me start. Remote sensing and GIS application in water resource management. So basically, what is the issue in India? We are 17% of world population, and we have only 4% of world's water resources. If you see the use of water in agriculture, it is almost 80 to 85%. If you compare with other segments like industrial use, only 8 to 10%, and domestic where people are talking a lot, it is only up to 7% only. But what is the issue here? The efficiency of irrigation is very poor. It is only 38 to 40%. But then there are a few more issues. If you look into the declining per capita availability, in 1947, our per capita availability was 5,200 meter cube per year, and currently it is around 1,400 meter cube per year. There are a few more issues like over exploitation of the groundwater, because in many places drinking water supply is not all through 24 hours. So people are digging the well and then they are using submersible pump and they are exploiting the groundwater, not only for drinking but for agriculture also. And of course there is a problem of the climate change. There is going to be increase in the extreme like floods and droughts. And finally, which is most important for our country, the population growth. So these are the some issues. Nevertheless, remote sensing plays major role in many aspects of water resource management. However, I would like to first emphasize on what are the current capability of India as far as satellite is concerned. If you see that the different orbits, for example, in geostationary orbit, which is around 36,000 kilometers away from here, we have satellites for telecommunication, but we also have the satellite for weather. For example, INSAT 3D, INSAT 3DR, Kalpana 1, these are the satellites which provide the information about the weather, for example, rainfall, then temperature, then humidity, then wind vector, all the information we get from this satellite. And this provides a lot of information as far as hydrology is concerned. There is a second orbit which we call a LEO. LEO stands for low Earth orbit, which is around 600 kilometers away from Earth. And all the remote sensing satellite, for example, Indian satellite, for example, ResourceSat or RESAT or CartoSat, all these satellites are basically at 600 kilometer altitude. Even to foreign satellite, if you look, see like Landsat, Spot, Sentinel, all these satellites are around 600 to 800 kilometers. And these satellites provide a lot of information about the Earth. They map the Earth, they monitor the Earth, and then we have airborne like aeroplane. That Dr. Daniel was explaining that how he is using aeroplane for mapping. But in our country, as and when required, we are using aeroplane. But nevertheless, UAV is the new, discovery. Like they are very much useful for very high resolution mapping. So these are the four important orbits where we are using the remote sensing sensors. Now, if you see what we get the information about the agriculture area. You look into this corner image, right corner, upper corner image. If you see, this is the agriculture area, and what you see that pinkish color, basically it is agriculture, and nice agriculture. Even dark, you can see individual trees are visible here, but you can see the barren agriculture land also, it is visible here. But then you can see also the forest area, even different type of species are also visible based on the tone and texture. And you can see the urban area, what is the settlement, what kind of settlement, what kind of, and also you can see the water resources, which I will explain in next slide. So basically we get the information like near real-time hydrological information. Means satellites are moving, we get almost every day a lot of information. So when, let us say there is a flood, so I can get not real time, but near real time. Suppose you want to know what is that land surface temperature. Yes, whenever satellite is passing, let us say today evening, then you will get the land surface temperature. Suppose you wanted to know what is the albedo, you will get the albedo within a day. So this is a near real time hydrological information. And because satellites moves around the earth, so you get the temporal information every 1 day, every 2 days, every 5 days, every 20 days, something like that. You have a special information like 10 meter, 5 meter resolution. So high resolution give you the more, detailed information, and low resolution will give you low detailed information, but it covers more area. And of course, satellite images will provide you the synoptic coverage. You want to map the entire command area, irrigation command area, which is around 200 kilometer or 300 kilometer by 300 kilometer. It is the only remote sensing which will give you the information in a single shot. Okay, so these are some advantage of the remote sensing which you will not get from the field data. However, we cannot avoid field information. They are also very important. I will come to that little later. So what are the current Indian capabilities as far as the remote sensing application is concerned? We have different kind of the satellites. For example, for land information and water information, we are having resource set satellite. This is basically is for land resource and water resources, and it has 3 sensors. List 3, the spatial resolution is 23.5 meter. List 4, spatial resolution is 5.8 meter multispectral, and VIAET spatial resolution is 56 meter. The advantage of all 3 is, for example, list 3, it covers around 140 kilometer by 140 kilometer of land area. List 4, it covers around 56 kilometer by 56 kilometer of land area. VIAET, this is very important. The spatial resolution is 56 meter, but it covers around 700 kilometer by 700 kilometer area. So you see entire command area you can map using the VIAET sensor. Then we have a microwave sensor for C-band, reset 1 and reset 2. Then we have a high resolution satellite, Cartosat 2 with 65 centimeter resolution, and Cartosat 3 with 25 centimeter resolution. And of course, our earlier satellite, Cartosat 1, was having 2.5 meter resolution. So all field level mapping you can do using this type of satellite. Then for ocean, because ocean, you know that Earth is 70% Earth is covered by ocean. So ocean influence land also. So we need a lot of parameters from ocean. For example, sea surface temperature, chlorophyll content, salinity of the ocean. These are very important for weather. And what you get, so we have a sensors like OCM, and then what you call SCATSAT, ROSA, and Saral altimeter we are also having. But then for weather, we are having many satellites like INSAT 3D, INSAT 3DR, which is currently working in Kalpana. And of course, Megatropic is basically it's a part of global precipitation mission. If you see the capability is with respect to the resolution, we have a resolution with less than 1 meter, like 25 centimeter to 1 kilometer. So all aspect you can cover, whether it is a irrigation command area mapping, whether it's a infrastructure mapping, whether it's a loss due to the flood, all these things you can cover using this set of satellites. Nevertheless, we have many foreign satellites also. So we are using, combination like Indian satellite or other foreign satellites as and when required. Now, what we get actually as far as water resources is concerned from remote sensing. So remote sensing provides us, for example, for precipitation, it is not directly providing the precipitation other than the precipitation radar. It provides us cloud cover, cloud top temperature, cloud motion vector, outgoing long wave radiation. And based on this, we get the information of the precipitation. However, there are two satellites, TRMM and GPM. They provide direct information of the rainfall and rainfall amount and intensity using the precipitation radar. Then for evapotranspiration, Dr. Daniel has in detail, he has discussed about it. He was telling about the net radiation, then soil heat flux and the sensible heat flux. Out of that, if you see, the soil heat flux is very important, and for that we need four very important parameters. One is the land surface temperature, which directly we get from the remote sensing. Albedo again we get from the remote sensing. Leaf area index and NDVI, these are the vegetation indices we get from the remote sensing. Then for water body, directly we get from the remote sensing. So we can do the reservoir mapping, reservoir monitoring, how much water is available in the reservoir, lake monitoring, ponds, flood mapping and monitoring. All these, I'll come one by one to all these aspects. Soil moisture, yes, we get surface soil moisture, not the subsurface soil moisture. Topography, which is very important as far as the modeling is concerned, as well as the hydrology, water movement is concerned. And we get directly from the remote sensing. Currently, we have different kind of digital elevation model from Cartosat-1, Indian satellite, we have Carto DM, but then from other satellites like we have SRTM or Aster DM, all these DMs are available. Then we get the slope from this aspect, flow direction and flow accumulation, which is very important for water movement on the ground. Then water demand for irrigation for agriculture, like crop acreage estimation, crop water requirement, irrigation water requirement, we get that indirectly from the remote sensing. When I'm talking about the crop water requirement, it gets directly from the evapotranspiration, and evapotranspiration you get from this net radiation, soil heat flux and sensible heat flux. So this is all, you know, there are many other parameters, but there are very important parameters which I have listed down. Now let us come to individual one by one. So you see the hydrological parameter, one most important one is the precipitation, because entire hydrological cycle governed by the precipitation, then precipitation coming down to the earth, intercepted by the canopy, then finally coming to the soil surface, then infiltration, subsurface flow, groundwater, deep percolation, then runoff, surface runoff, that storage in the depressions, storage in the reservoir, lake and ponds. So the precipitation, how to measure precipitation. So as I told you, indirectly from all these satellites, this optical band, NIR band you can get. But if you have a microwave sensors like PR, precipitation radar and TRMM, directly you can measure the rainfall. But you know, there is a constellation of the satellites, they move around the earth, and like TRMM, then GPM, there are four observatory, then our Indian satellite like Megatropics. There are many satellites moving around the earth, and we measure the precipitation. So this is the GPM, basically it's a core observatory launched by the NASA, but we are the party of it, and we have a Megatropics. And you will know that they are having the dual frequency precipitation radar, which measures the rainfall content, amount of the rainfall and the intensity. And of course, passive microwave imager GMI is also there. So this is one example, like that all the GPM data is merged for entire country. And during the monsoon period, all the data products are merged, and you can get the rainfall products every 3 days. So this information can be utilized for the water balance for the country. Now, this is water body mapping, and you know the water appears very different than other features. You are aware about the remote sensing. When I generate a false color composite, all the red area appears to be this is vegetation basically. However, the type of vegetation is different. For example, if you look at these dark patches, they are the forest. If you look at this pinkish color, they are basically nice agriculture area. So here also you can see the forest plantation as well as the agriculture area. What is important here as far as water resources is concerned, look at this. This is a big water body. It's a bluish color, big water body. So this is basically reservoir. This is another reservoir, but there are some small water bodies. They are basically lakes and ponds. So you can map in a single shot, in a single imagery. You can map reservoir if it is there, the lake, the pond. What extra you can see here, that quality of the water. If you look at the reservoir, Krishna reservoir here, you see here, this is dark tone, while here it is a bright tone. So this is this is more sedimentation here, this is less sedimentation here. Similarly, if you compare with the ponds and lakes, you see less sedimentation, but you see a lot of sedimentation is here. Another very important thing what you find here, you can see there is a link canal from Krishna Reservoir to Velugadi Reservoir, and this link canal is linking between these two reservoirs, but there is a uptake of the canal which is irrigating this area. So you see the entire, you see the reservoir, the lake, pond, you see the irrigation command for agriculture. So all these information with a single shot, you will with a single image, you can get from the remote sensing. Now, what other advantage of water body mapping is the reservoir monitoring. Look at this. This is one example of Mula Dam. You can see this is the dam here. This is the river, and this is the dam here. This is the dam site, and this is the backwater of the reservoir. You can see in the October in India, basically after monsoon. So all the reservoirs are full, and you can see this is the dam, and this is the backwater. You can see spread area of the water. This blue color, dark blue color is the water basically. So nice, But then what happens after that? You are utilizing this water for irrigation, for hydropower. So then how this water is depleting, you have to monitor it. So for example, you can see December. If you compare with earlier image, let us focus on this side. And you can see here now in December it is reduced, isn't it? In November it is more here, and in December it is reduced. Now, if you come to the March, you see further it is reduced. You compare with December, now you see lot of water is there. Now, March it is further reduced, not only here, everywhere. Okay, if you carefully see all the places, look at this point. Okay, now look at this point, it is reduced. So it is reduced, basically that water is going away. And then you look at this May, it is completely, backwater is completely reduced to become a river now. Look at this, now compare with this. Okay, so you see this is how we monitor, and the advantage, what is the application of this type of monitoring? The application is reservoir operation. If I know how much water is available, then I can operate reservoir judicially for irrigation and for hydropower. So this is very much useful for information for hydropower generation, irrigation water diversion, and drinking. If it is feeding to a city, then drinking water supply. Now next, for flood, also we map the water body, and look at this. This is the integration of satellite image and GIS layer for flood mapping. And what you see here, that this is a GIS layer, district boundaries overlaid over the flood boundary. This blue cyan color, basically it is a flood water. And what you see here, but immediately you will find out which district is affected. This is Assam state, and you can see Barpeta district is affected, Nalbari district is affected, the Darang district is affected, and Marigaon district is affected. And if you take out one district, let us say take out this Marigaon district, and you superimpose over the village boundary, then what you see here, look at this, a flood layer, village layer, integrate in the GIS, and look at this. This is the flood area of the Marigaon district, and this is the village boundary, and this is the actual photograph. This is a flooded area, and immediately in GIS environment you will get how many villages are affected. If you have an attribute, the name of the villages, that also you can find out, and you can start working for the relief and rescue. And if you look at this, immediately it was calculated, and we found the village affected. Total 465 villages in this Marigaon districts are affected. And in NRSC is the nodal agency to provide such type of information during flood, and turnout time, TOT, is around 4 to 5 hours once they receive the satellite imagery. Means once they receive the satellite imagery, within 4 to 5 hours, they provide all these information to the Government of India, Relief Commissioner and District Collectors. Now this is another water body mapping, and recently it has happened. You know that India was locked down from 25th March, and we have carried out a study in Dehradun for various places of Ganga Basin. It started from Haridwar, then Delhi, then Kanpur, then Prayagraj, then Varanasi. I am showing one result of Kanpur. You can see this, as I told you, the quality of the water. If it is a darker blue or black, it is pure water. And if it is, bluish, it's not a pure water. There is a sedimentation. And look at it, the turbidity here. This is March 19 of 2020, before the lockdown. You see this water quality. And this is the April 3. Lockdown started from 25th March. And April 3, you find the water quality has improved. Why it has improved? Then is further we have analyzed it and we found all factories were closed. So there was no pollution is coming to this, this river. Then next, let us go to the RS application in irrigation command area mapping, which is very, very important for efficient agriculture management. Okay, so there are different satellites, as I told you, there are different sensors. So we have like ABIPS, as I told you, 56 meter by 56 meter. If you are mapping entire command area, and this resolution is very good, you will get the crop acreage. So this is having the resource set 1 and 2. SWAT is 740 kilometer, means in a single shot you can cover 740 kilometer by 740 kilometer, and repeativity is around 5 to 7 days. So you say that with every 5 days you can map your entire irrigation command. So what you map, main canal having width of around 50 meter or more. These sensors give high coverage and high temperature resolution, so may be best useful for monitoring of the crop acreage, crop area, crop type. Then we have a list 3. Then SWAT is around 140 kilometer by 140 kilometer, and repeativity is 24 days. They are good for mapping for main canal, branch canal, distributaries, having width around 20 meter or more. These sensors give high coverage and high temperature resolution, so best suitable for, actually if you want to map village level or taluk level crop acreage estimation, then this sensor is very good. Now let us go to another sensor, list 4. This is another multispectral data it provides with 5.8 meter. This is the SWAT is 24 kilometer by 24 kilometer, repeativity is 5 days, and you can field level mapping you can do using this satellite. Then we have a Cartosat 1. This is the panchromatic 2.5 meter by 2.5 meter. SWAT is 30 kilometer. Then this you can individual canal, minor canal, it can go. I'm sorry, it is written receptivity, basically it's a repeativity. Then we have a Cartosat 2B with 1 meter resolution. You can see so much detailed information you will get. But of course, Cartosat 3 with 25 centimeter resolution, you will get detailed data. Now look at this, how you will map a irrigation command. So this is one example of our Upper Ganga Canal. This is seen by extra data from space. And you can see here, this is the Haridwar city. And this is that, river is flowing, Ganga river is flowing. And you can see there is a stoppage of this water. Basically, this is a barrage. We call it a Bhimgoda barrage. And there is a diversion of the water. What do you see here? Diversion. And this is the Upper Ganga Canal. So this is the main canal you can see, and this is the all agriculture area. And there are various, seasonal rivers are also. But the question arises, all these interpretation I am doing, can I have a better picture of it? Yes, with high resolution data, you can have a better picture. So let us see, with 5.8 meter resolution, you can see not only the minor canal, but also you can see individual agriculture plot, right? It is visible here. But beyond that, what you can see? Now, look at that. I told you that Bhimgoda barrage of Haridwar. Now, this is the 65 centimeter quickweather data. And what you see here? A barrage, a diversion structure for canal, even a bridge also is visible. So if you are having a 65 centimeter data, individual structure you can see. Okay, let us move further. You can see the branching of the canal. This is the main canal, and this is the branching of the canal. Okay, and this is a bridge over the canal. This is all settlement area. Further, you can see some more detailed structures like aqueduct and superpassage. Basically, aqueduct is a structure which is built over the river if canal is flowing over the river. But if river is flowing over the canal, then we have to construct the superpassage. And this is one example. The river is flowing over the canal. So this is the superpassage, and you can see this structure. And this is the energy dissipating structure. And huge water whenever this is basically seasonal river, and river is flowing. During the season, whenever there is a heavy rain, river is flowing. So we have to reduce that what do you call energy. So this is the superpassage. Energy dissipating structures are visible, and all these maps you can created using the remote sensing data. So what is the advantage? You can map entire irrigation command, not only with respect to the irrigation water requirement, crop acreage estimation, but also the infrastructure mapping. So Government of India has given this task to the ISRO and RSC, that we have covered around 53 irrigation projects from 18 states in phase 1. In phase 2, 50 projects, and currently phase 3 is going on. And this is the area which covered by IIRS Dehradun. So I have mentioned, and I want to show you now detailed how we map using the Cartosat-1 data, the gap areas in canal. So generally the government is giving fund for canal structures and canal. You can map individual canal structure, not only that gap area. For example, here the canal is constructed this side and that side, but there is a gap area here. So all these things you can see, there is a gap area here. There is a gap area. There is a field photograph. What is the region of gap area? So all these things you can detect from the remote sensing data. So based on that, you can create irrigation potential created or irrigation potential actually utilized. Then remote sensing for watershed monitoring. So this is the, you can see this is the field data, the satellite data and the actual field. For example, if you have a high resolution satellite data, look at this. This is the pond, but actual field photograph is this. Very nicely it is visible in high resolution data. But what is this? This is the contour trenching. Look at this. Of course, this is further zoomed to this. But if you see here, this is a multispectral. So you see, these are the contour trenching. You can see here, this is a field photograph. This is the actual from the, this is contour trenching. This is the contour trenching. Detailed information you will get using the high resolution data. So basically what we are doing, suppose you are going for watershed management plan. So before management plan, we see the satellite image, and after implementing the plan, we see the satellite image, and we can find out what kind of execution you have done as far as watershed management is concerned. What is the contour trenching, contour bunding, check dams, ponds you have given for that area. So this is nice tool for watershed monitoring. Now look at this. This is a little old, but anyway, this is very important. I want to show you. Look at this. Before the project, you see there is nothing is visible here, but after the project, you will find check dam. Before the project, no check dam. After the project, check dam is visible because water body is there. So it's a spread area of the check dam. Then before the project, after the project. But second thing also you will find, whenever there is a check dam, irrigation agriculture area has increased. Obviously, because a lot of water is available. So such type of information you will get from the remote sensing. Now look at this. If you have a high resolution data, this is before concentrate here. Let us please concentrate here. You see a circle. Nothing is visible, but you see the field bund has been provided, and these bunds are visible using the remote sensing data. So this type of monitoring of your agriculture area, look at here also before and after, how much you see this, all bunding, field bunding has been created because agriculture field, they were utilized for proper agriculture, production, and before you see nothing is there. So this type of monitoring can be done using the remote sensing data. But then another question is, a lot of water shortage is there, water is wasting during heavy monsoon, but after that there is no water. So I have to find out the suitable site for water harvesting. So how to do that using the remote sensing and GIS? This is one classical example, and this is a very good example for how to implement your plan. So for example, how to achieve this? So first we should have a different type of map. For example, soil map. Why we need a soil map for site suitability for check dam? Because soil, I cannot construct a check dam in the sandy soil. It should have a low permeable soil. So I need a soil map. Similarly, land use. I need a land use because I cannot construct check dam on any land use. It should be agriculture area or nearby agriculture area. So I need a land use, land cover. Slope. Slope is needed because for check dam, it is important. I should not construct check dam in a steep slope or moderate slope, slower area or shallow slope. I should construct a check dam in a moderate slope. So slope is also very important. And of course, where should to construct a check dam? Check dam has to construct it on the drainage. And we should have a drainage map with the drainage order, because I cannot construct this check dam on the more than third order drainage. Once I have all these layers in GIS environment, I superimpose using the multi-criteria analysis. I will find out the check dam. So with this analysis, we have find out the 3 check dam in this area. This is a site suitable. But we further move into it. What we have done with these 3 check dam, we assume some height. Okay, we can construct up to this height check dam based on the digital elevation model. And we have calculated how much area what will be the water spread area and what will be the volume of water collected using this hydrological modeling. And we found in this check dam, number 1, this much area will be covered. Check dam 2, this much area. Then we convert it to GIS. It is very easy to convert the spread area if you have a DM to convert into the volume. And we find out in check dam 1, the volume is 40.46 million cubic meter. In check dam 2, the volume collected was 0.04 million cubic meter. And in check dam 3, the volume collected was 0.5 million cubic meter. So what is the use of this analysis? The use of this analysis, if I know this much water is available after the monsoon, I can plan this much water can be irrigated. This much water can be utilized to irrigate how much of land. For example, near to this check dam, I found some agriculture area. So a farmer can utilize this water. Let us say he is growing wheat crop, because it's a Rabi season in India. Wheat crop is a winter crop. So he is going for the wheat crop. So I know the delta of the wheat crop. Okay, so I know the delta, I know the volume, so I can find out how much area it can irrigate. So this type of planning you can do in your watershed using the remote sensing and GIS. Then let us move further. Snow cover is very important because India is covered by mountains with lot of snow cover, and it is very difficult to get the snow cover, and snow melt give very important input. For example, Ganga River originated from the Gangotri Gomukh Glacier, and this entire Ganga water, so a lot of water is coming basically from snow melt during the lean period. So how to get the snow cover area? Now this is the one example using the remote sensing data. Here white color is basically snow cover. Okay, so in all images, so you see the my image, you will find lot of snow cover is there. June it is reduced. So why it is reduced? Because of the snow melt. Then October, basically October we have a minimum snow cover area because after June temperature June temperature increases as well as the heavy rainfall occurs. So melting is very high. So October you have a minimum snow cover area. November it is further increased. Carefully if you see, December it is further increased, but in February further increased. Generally in the month of February, and especially in the month of February and of March, we have a maximum snow cover area in our Himalaya. Then May it is reduced, June it is further reduced, July it is reduced, September reduced, October reduced, November reduced, and then again it will start increasing. So this kind of monitoring can be done. But this monitoring is very important input for hydrological model. So look at this. This monitoring we are doing using such type of graphs. These graphs are generated from these maps only. For example, look at this blue line. In the month of October, almost 0 snow cover area in that particular band. Band means elevation. And in the month of February, it reaches up to 80%. And then in the month of again September, it reduced it to 0. So from where, from how this area, so from 86 or 84% to 0. So where this snow has gone, it has melted. And this input is required for this type of model. This is the simple normal SRM model where this snow cover area is very important parameter. And then we put into this model and we generate the hydrograph at the outlet of the dam. So this we get how much water is coming in a reservoir using the remote sensing. And this is the example of estimated and real. So we have estimated and this is the real. So you see the accuracy. Currently our accuracy is very high. In fact, we are doing for Beas Basin or Gangotri Basin regularly. Okay, but then this is one basin I have told you, but not only that, we are covering entire, Northwest Himalaya using the remote sensing. What we are doing, we are using the AWS data, MODIS data. Every week, we are generating the snow cover map for entire country. And this map is used for entire Northwest, not country, entire Northwest Himalaya. India is a very big country, so I'm talking about Northwest Himalaya. And you can see we started from 2000 onwards, basically. So we have now data for more than 19 years for this area. But then the glacier, so whenever we are talking there is a glacier, there is a retreat also because of the climate change. But it is not only the retreat, we have to see the health of the glacier. Means we should be able to map the accumulation area, ablation zone. So you can see using the recent microwave data, we could able to get a snout where the water starts, or that ablation zone where there is a depletion of the snow, and the accumulation zone where there is a accumulation of the ice. So all these zones, whether it is increasing, decreasing, that shows the health of the glacier. And with this satellite image, you can find out that this glacier can be mapped so nicely using the microwave data. Now, finally, I'm coming to the modeling. Basically, whenever we are talking about the remote sensing, there are three M. M1, we call MQ. So first M is for mapping. I have shown you. Second M is for monitoring. Already I have shown you how to monitor. And third M is for modeling. So mapping, monitoring, and modeling. That is a key buzzword for the geospatial technology, especially the remote sensing and GIS. Okay, so we have to do the modeling. So we have done this study in IRS Dehradun. We have covered all 20 river basin of the India. This is the map, Indian map, and all basins are, see here, you can see. What we have done, we have divided all basins into the grid. For example, if you look into the one grid of Pennar Basin, Pennar and nearby rivers, so all basins divided into 25 kilometer by 25 kilometer grid. Then we use the model, and this model is a basically variable infiltration capacity model. And what we are doing here, we are doing, energy balance component as well as the water balance component. For example, evapotranspiration, we are calculating using, energy balance approach. Like we are getting that latent heat flux, net radiation, canopy evaporation, transpiration, evaporation from the barren soil or different surfaces, water surface, and soil heat flux. All these things we are calculating. Not only that, we are calculating the runoff. Or finally, we are. So what is the input basically for each grid? In fact, we are calculating for each grid, and for each grid. So it means we are covering entire India, but now we are covering the entire India, but we are calculating this thing for each grid, and there is any variability within each grid also, because this is a 25 kilometer by 25 kilometer grid. And you will ask me, in this there are different kind of land use land cover. For example, there will be forest, there will be agriculture area, there will be water body in a 25 kilometer by 25 kilometer. There will be, what you call urban area. So what we are doing, this is the subgrid variability. Like this is one model actually. This model is developed by Washington University. So you can see here that subsurface variability we consider, and water balance is calculated based on this individual land use land cover. So, but what is the input? This is important. So from remote sensing, we get the vegetation type, vegetation fraction, we get the NDVI, we get that LAI, all these information we are getting. Topography we get from remote sensing. Then, different soil parameter like, land surface, all these parameters we are getting from remote sensing. Then rainfall we get from remote sensing. Then of course, minimum maximum temperature, all these information we are getting. We are putting in the model, and finally we are getting every day for each grid for entire India, we are getting the surface runoff, evapotranspiration, soil moisture, and base flow. So you see every day, every grid for every all the basins for entire India, we are calculating these parameters in Dehradun. So till some papers we have published already, and we are now next paper we are publishing. So this is one example. It's an old example because this paper is published in the current science. This is a 15 years runoff potential map of India from 91 to 2005. And so we get, runoff for every day for 15 years. Now we have calculated from 2006 to 2016 also. Again, we are publishing this paper. So now, in fact, we are trying to automate this. So automatically, our server is generating this type of maps. Now, finally, that the flood mapping already I have told you flood modeling. These are my few last slides. a few of the last slides. So this is, we are working in Dehradun. What we are doing basically, Northwest Himalaya, a lot of, heavy rains, cloudbursts are there. So if I am getting that, I'm using the WRF model. Again, I'm getting from IMD also, out at IRLs also, we are using WRF model. This is a weather research forecasting model. It provides me next 3 days rainfall. Then we have established a hydrological model. So we are using Prayagraj. Then we are also using the Mike 11 and Mike flood. So we have developed the model and we established the model in the entire basin. So you see this model is established and we are generating the hydrograph like that. So one example I want to give you, not only for Northwest Himalaya, you may be remembering last year there was a huge flood in Kerala. So you see, this is the, if you see the down, you see this is the actual field photograph. Okay, this is the actual field photograph. But if you compare, I compare with my modeling, and you see this is our modeling. Of course, this is the depth of the water. So this is our modeling, and this is the actual field photograph, and how closely it is matching. Similarly, here also you see the bridge during the flood, and you see the bridge here. So you see that this hydrological modeling in prediction or flood modeling is really helping us to know how much water is coming to my area so that I can be prepared for any disaster. So this is all about my presentation, but finally I'm showing you the last slide, which is the key and crux of the utilization of geospatial technology for water resources. What I'm telling you here, it is not only the remote sensing data. There are various other things which is important. For example, you need GPS. For all these maps I've generated, georeferencing, I need a GPS. Location-based services, information, I need GPS. Field data collection, I should have. For example, how to get the KC, how to get the crop acreage. It is one, yes, you are right, or crop yield. One is from remote sensing, but you should have a crop cutting experiment. So you need a field data. Similarly, internet information for communication. Altimetry is required for elevation, not only for elevation DEM, but also it is required for water level. Then, of course, digital elevation model for more accurate total station. 3D view generation, photogrammetry, visualization. These flood maps, I have given you some visualization. It comes from photogrammetry. So basically, when you are going for geospatial technology for water resources or agriculture, convergence of these all technologies are required. And once you converge all the technology, you get a viable solution for implementation. So this is my final message. Thank you very much.
Thank you, Dr. Agrawal, for your valuable presentation. Now, let's welcome our next speaker, Dr. Manjul Hajarika from Thailand. Dr. Hajarika is Director of Geoinformatics Center at Asian Institute of Technology at Bangkok, Thailand. He is alumnus of IIT Kharagpur, the AIT, and also University of Tokyo, Japan. He has nearly 3 decades of experience in remote sensing and GIS and its application in disaster risk management. Dr. Hajarika will provide his insight on geoinformatics in agriculture. So let's grab this opportunity. Dr. Hajarika.
Yeah. Can you hear me?
Yeah.
Okay, thank you, Dr. Mishra. It's a great opportunity for me to tell what we are doing here in AIT Bangkok. And I'll have a little bit another meeting after this. I'll straight away go to my presentation. So I'll share my screen. Just one moment. Can I just one? I am. take a little time. Okay, yeah. Can you see my presentation now? Hello?
Now we can hear you.
Okay, thank you. Thank you. Okay, my presentation is application of geoinformatics in agriculture. And I will cover my contents will be a little bit of introduction. Maybe there are a lot of students also. So I thought that it will be better to give a little bit of introduction. Then I'll talk about satellite data in crop monitoring and yield forecasting. Then I'll talk about use of drones in crop monitoring and yield forecasting. Again, I'll talk about advances and application of big data in agriculture. And also finally, I touch upon some, we have developed some models for agroecological zonation using these technologies and for crop suitability mapping. So there's an increasing role of data in smart farming. There are three things. You can see one is your smart sensing and monitoring. Okay, so there are satellite and other things. And we have also smart analyzing and planning using the data wherever coming, and also IoT under smart controlling of things. And all these things you can see in the middle is cloud-based event, cloud-based event and data management system. So this is the main how these technologies are coming into operation, and this has been quite exciting, I would say. So data acquisition platform, there are mainly the first one originally was surveying by ground. Then aeroplanes were used. Then we got the satellites, and now the latest one is drones. So I'll give a quick overview about the, let us talk about satellite data, where you can, these are extensive coverage you can have and wide spectral capabilities. Then, but this data is expensive if you go for high resolution data, but low resolution, even a lot of data are free. Relatively low resolution, 30 centimeter, you can go. Some commercial satellite is available now up to that level. And also data acquisition maybe weekly, bi-weekly, like that. But if you go to the drone, which is image acquisition is on demand. Whenever you want to get image, you can get very high resolution, up to 1-2 centimeter is possible. Unaffected by cloud cover, where satellite has a problem of cloud cover. We don't have this one.
So excuse me, Dr. Azariga, sorry to disturb. I think your slide's not moving, and kindly take it in a presentation mode.
I'm in presentation mode. Can you see me?
Not yet in a presentation mode, sir.
It is already in presentation mode. Just one minute.
If you can click, sir, once again, I think it will come.
Just let me put it again. Can you see now? I mean, if I don't use as a presentation, maybe
Now we can see.
You can see, right? So let us put it only in this mode. Maybe this is better, I think. You can see right now? Yeah. So let's do in this way. Let me increase a little bit. Right? Okay. So this is drone I was talking about. The drone is, but the disadvantage of drone is a relatively small area coverage, and drone regulations can restrict the usage of this, which is the case in India as of today. Law is coming up. Then operation is susceptible to weather like high wind or rain, that kind of things. So I will go to the satellite data for crop monitoring and yield forecasting. It is in Uttar Pradesh only. We did a work for World Bank, and where we are using NDVI. Many of you already know. I'm not going to explain NDVI, but it is basically telling you how greenness of a crop or a forest or whatever. So this is NDVI of whole Uttar Pradesh during Kharif season, which is rice growing season, and you see this dark blue color. These are the very high NDVI, and what happens is we develop some yield model for this NDVI, and we calculate the possible yield based on NDVI. So you can see in the year 2001 to up to 2013, you have this actual rice production, and these are predicted. So basically what we do is this NDVI is available every 8 days from Modi's satellite. So every 8 days in 250 meter. So the advantage is that if you have as you know, Modi's satellite comes 2 times a day. So if you there is 16 passes of satellite in 8 days. So you have the high chance of getting some cloud-free images in this, because it's a rainy season. So what happens is if satellite come today and there is a cloud in that particular location, tomorrow it may not be there. So that's how for 16 days all the cloud-free areas are taken in together and make it cloud-free image. And you can see, but we have to develop some yield model, and we have this yield information for 2001 till every year we have, and we have also every 8 days for satellite NDVI data. And you can we develop the yield model. Then you see once you develop the yield model, then you can see 2002 and 3 there is a actual production is 68,752, but predicted is 71,657 tons of tons of rice. Now what is happening is this predicted one coming before harvesting just is become from green to golden color. So you know the actual yield comes after 6 to 8 months, because they do a lot of crop cutting experiment, take samples, and all this statistical analysis takes 6 months to 8 months time. So what we are doing is at the time of harvesting, you are getting this information. So this is very, very important, so that you can decide about export and import. In case of India, that is not a very important case, because we have over production of rice and wheat. But in some countries like Bangladesh and many countries, this is very, very important information. And at the time of harvesting, if in terms of prices is low, and you can get, if you think that your production is less, and you immediately go for procurement. Otherwise, price might go up. Right? So this kind of we did for, and also since every 8 days we are monitoring, so you can see the date of start date of rice or growing. So this yellow one is May, blue one is June, and red one is July, depending on the water availability, whether it's irrigation or rainfall. So and also we can see the single crop or double crop, because particularly double crop more, single crop, red one is single crop, green one is double crop. Triple crop is very, very limited, very few spots, but a double crop basically rice and wheat, you can see. So this is, we also did the similar thing in Assam, 2 districts, and you can see the blue one is actual production and red one is the predicted one. It's quite, trend is very good. And this is, we did not do any field work. We're sitting in Bangkok, we did this. So if we do field work, probably this will be further improved. And this is, I think, quite good 6 months before you are getting this information. So it is quite helpful for the decision making. This is in Bangladesh, very good, I would say, very close. This is in Cambodia. Now I'll talk about the same thing. We use drones for rice monitoring here in Thailand. And we have these 3 drones. All of 3 are developed by us. We assemble drones here and we fly. And the first one is RTK drone, which is very high accuracy, but multi-rotor. But this one is, second one is fixed wing, which can fly up to 90 minutes, around 90 to 100 minutes, around 90 to 100 kilometer it can go. And this one is hybrid between the third one is VTOL, hybrid between these 2, because the fixed wing has a problem of landing. You need a landing space. Kind of runway. So if you combine them, then this is vertical takeoff and vertical landing, we call VTOL. So we are using different sensors, normal camera, we are using DJI Phantom also. Then these are the Parrot Sequoia, which we have for multispectral, like a satellite kind of sensor band, 3-4 bands there. So some of these, I got some of these satellite, drone data you can use for monitoring large plantations, because if a large plantation, like for example, tea gardens in Assam or coffee gardens in some parts of the country, it is a large area, so it's very difficult to monitor manually, or even satellite also. Regular monitoring is difficult, but I think using drone you can get very high resolution satellite and high resolution images, which you can see if there's a base attack. You can use probably most likely this multispectral camera. So if you just look at the NDVI, if there's an NDVI is less, maybe base attack or disease, you can. This is also very high resolution satellite, drone image. You can see the invasive species or weeds coming into the crop field. Also, you can, using drone, you can also have maintained a crop database, because you regularly fly and you can see the situation at a regular interval, very high resolution images. So you can identify if there's a problem, then what should be done. And also, this is a large scale plantation. I think crop database at a regular interval is very, very important for management of the crop. This is coconut plantation. You can see each tree here, and you can, using some certain algorithm, you can actually count the coconut, how many coconuts are there. And this is also very extensively used for oil palm plantations in Malaysia, in Indonesia, because this tree are 6, 7, 8 meter high. So it's very difficult for farmers to know the condition of the crop. So if you fly, you can see the crop condition, if whether they are healthy enough or not. The same thing, you can also determine the crop density, plantation density, and counting. And if there's a gap, you can fill using this kind of drone images. Also, one of the advantages of drone is that you can get a very high quality elevation model, which is otherwise very, very difficult. With satellite data, those are plus minus 10 meter error. But there are some commercial satellites like Airbus, they have a good elevation model, but still not at this level. So if you know the tree height, you can also estimate the biomass, provided you do some ground truthing for a particular area of forest. You can come up with very, very good good estimates. We did something in Nepal forest. It was quite good then, using optical has very, very limitation, but using SAR data, you can do this kind of this kind of things. But still drone data is much better. So this rice monitoring work we did in Thailand. These are 16 plots, and you can see from 1 to 16. One is no fertilizer, and gradually we increase the fertilizer, and then we have different control of all these plots. And you can see the rice growing, and its NDVI is increasing, and where it is peak, after that it become yellow. So we fly the drone every 10 days during this growing period. So these are the rice plots, 16 plots, and see here this red box, there is not good crop. Something has happened in this area. So you can monitor the crop in details. And also if there is some weeds are coming, this can be also, you can see in these images. Similarly, we have this multispectral camera in the drone. So you can see the NDVI, the red color, dark brown, this is high NDVI. You can see here, or this area also. You can see very. So then we construct this spectral curve, and you can see that as time increases, then this is NDVI is increasing, then peak, and then it goes down and becomes some kind of constant. And we use some yield data earlier, and we can have this yield and NDVI relation. This is very similar to satellite, but we just try to. But I think the idea here is not to monitor rice for a large area using drone, because this is difficult. So what we want to do is we use satellite data, this 8-day satellite data, monitor the rice. If we see there is some problem in some location, maybe NDVI has gone down, then we can fly a drone and see what is exactly happening in that particular area, whether there is a pest, disease, or some other problem. This is about drone, and I am going to talk about some application in big data in agriculture. So some of you might have know about, there is a platform, very completely open source platform. It's called Send2Agri platform by European Space Agency, which basically use Sentinel data, Sentinel-2 10-meter data, as well as the Landsat TM 30-meter data. And this is very dedicated for agriculture. And it automates typical remote sensing tasks in like downloading, atmospheric correction, geometric correction, everything will be done automatically. So once you establish this platform in your server, in your university or agency, you install you download the whole package, and then you set up according to your requirement. You may set up, okay, only you want to see agriculture in a particular district, or for the whole state, or for the whole country. You have to give that, but you have to define that one. Then what interval you want to do that, a month, weekly, or 2 weeks, or monthly. And then it will be also, you need some ground data, for example, which are the area, say rice area or wheat area or some other area, sugarcane area. So all those, some of the ground information will be need to be given. And then once you establish this one, every say you set every 15 days. So every 15 days your crop conditions will be produced automatically by this system. You don't have to really do anything. So basically, this composite of cloud-free data, all data sets are available in the Send2Agri in European Space Agency. Then this crop mask will be developed using some ground data. Satellite also do the crop, they will do automatically this cropping area, but using ground data, you need to modify or fine tune this crop mask. And this is dynamic. I mean, as crop is changing, increasing the area, so it will automatically capture by the satellite data. Once you put all this relevant ground data, then you can different type of crops as rice or some sugarcane or others. It will be monitored, and you can get the NDVI, leaf area index, all those information every, as I said, maybe every week or every 15 days, whatever you said. So this is many of the international organizations like World Food Program is using this this kind of platform, and all satellite data is coming here, and ground truth is coming from mobile phone applications. They have a mobile phone. Then you produce system will produce these crop maps and other information. So, for example, you can weekly or monthly or bi-monthly cloud-free images 10 to 20 meter spatial resolution, biophysical parameters like NDVI or leaf area index, and every weekly or monthly dynamic crop mask. For example, you are, as I mentioned earlier, that rice crop, some is sown in May, some is in June, or some in July. So it's dynamic. This rice area is increasing because of depending on the rainfall or depending on the irrigation facilities. So this kind of, once you have this mask, a basic mask is ready, the system will automatically capture all these dynamic things within that. And cultivar also crop type map you will get, and crop yield forecasting you will get. So this is one example. There are 3 areas, A, B, C in Australia, and you can see they are monitoring like barley, chickpeas, sorghum, oats, canola, cotton, wheat. They are different using this system. Also, this is some work done is in Bangladesh, then in Yukui in Mexico, and Iran, Malawi. So you can look at the accuracy; it's quite good accuracy, 90% accuracy in some cases. Yeah, more than 90, 99 here. So once you establish this one, it will be very, very useful. And good thing is that we don't need any software to buy, or you need a good computing system and you need a very good internet. And all this, once you set the parameters, even some of the parameters, this agricultural specialists, or you can discuss with them, and then you can set the parameter. Once you set the parameters, set for your state or your country, and you regularly get all this information without doing anything. Everything is automatic, end-to-end automatic system. So this is the same platform we install in AIT. Now we are monitoring crop in Thailand. We plan to monitor in Bhutan as well as Myanmar and Laos. And let's see how successful we can do, but it's an ongoing process now. This is agriculture ecological zonation map, which we developed. Actually, this agricultural ecological zonation is a FAO work. They started in 1978. And they have developed till recently quite a good methodology. But problem was that it was they did not bring it to GIS. So they use in some old programming language, probably some of you know, like Pascal. When I was in IIT 1989, 90, I used Pascal. So that was developed in Pascal language, which is now dead, I think. So now we take all these things and we reprogram everything in Python, and we develop this system, and in special geospatial format. So this framework is you have all climate data, rainfall, temperature, humidity, all this, and soil data you have terrain data, elevation, crop parameters you have, and you go to the system, and then you do 2 things. One is crop suitability as well as crop yield. So, for example, this is we have done in Laos. So this whole country is divided into grids, and the size of the grid depend on what are their input parameters, grid size. I mean, that's rainfall or soil parameter, whatever. And then from January 1 to December 31st. So we know the temperature, rainfall for each cell every day, humidity, we know all this information is there. Then we put say 10 or 5 dominant crop or 10 dominant, whatever you put there. Then you simulate that if with this rainfall condition, climatic conditions, soil conditions, these crops will be simulated, growth there. And you can see how good they are growing. And then after simulation, you can see that, okay, this crop is giving this yield, or the, these are the, you can see the calculate total biomass crop yield, then calculate effects of limitation on crop, water limitation in crop yield, calculate the effect of soil terrain properties on the crop yield. So also exclude area crop which are not suitable with respect to temperature or water limitation or slope. So those kind of things, everything it can be done. And you can see this is for Laos, different growing period of length. So this red one is you can grow for longest growing period because of sufficient sunshine or water available, those kind of things. And then crop suitability for different, so this red part is highly suitable for crops, different crops. And also you can see the estimated yield. So high suitability means high yield in the upper part here. And also multi-cropping, you can see some cases you can go for single cropping, some cases you can go for double cropping or triple cropping even. And this can, so you can get a, what are the best crop, where you can do single cropping, where you can do double cropping, where all this can be calculated in GIS platform using this one. So it is, FAO has taken up, and we are now implementing in Afghanistan now. And FAO has a plan to implement in several other countries. So particularly those who are a little bit not so much have national agricultural program, strong agricultural program. So Laos, maybe Afghanistan, some of the other countries will be implementing as per the request coming from FAO. And you can see the value, we try to validate, it also evapotranspiration expression is calculated. You can see millimeter per day, our results, and this is other two from ground data. And so it's very, very close up to the first decimal or second decimal. It's quite very good results we have got. This is some maize data estimation from the yield. Our estimation is 7.27. Reference yield is 7.5, so very close. I mean, almost same. So this kind of accuracy you can get. So I think it's a very good tool to implement. And this will be made, I think, free by FAO, acknowledging us. And I think this is I got from FAO recently, because I am also part of the FAO team here, regional office here, FAO. I mean, we are helping them technically. So recent one of the presentation, this is given by FAO, Future Outlook. So I think this is going to be, they're talking about small farms with all gadgets. So I think this might suit for India because we have small land holdings, but the problem is the farmers are not, I mean, a new generation is not very much willing to work in the farm. Farmer's son, maybe he wants to do something else, not really, because it's hard work and not so much return, as we know. On the Prime Minister is saying doubling the crop, how to do that? So that's a big challenge. I think this is very important that at this point of time, our agricultural graduates, engineering graduates, if they take farming as a choice, And if these kind of high-tech things, I'm pretty sure a lot of young our engineers or agricultural graduates will be take up. So here you can see this is control room. A farmer, he's looking, all drones are going monitoring things. You have they are coined a new term called agri-bots. So these are agricultural robots, small robots. It will do the operation in the field. Drone will do the survey. Your smart tractors, you don't have a driver, automatically is plowing and things. And also monitoring the cow with sensors in the cow. And also, even I was recently, there's a presentation from Tafe, the tractor company in India, chairman. Recently, I heard that he was talking about that. This life of how long tractor will be in the market is a big question now, because you don't need to really put a seed. You are using a tractor and you are using a lot of energy for plowing and all, but it's not necessary actually. So there are some drones are coming, which is a seed is put in a capsule and drone flies and it shoot and it goes to 5-6 centimeter in the ground and break it. The cell is break and there is all necessary fertilizer or pesticide, whatever it is in the seed itself. So I think future is very, very exciting if we can go to this kind of things. And I hope this will be, our graduates will consider this kind of farming, and probably organic farming and others. High value farming can be done. And this is, I just wanted to show this, this particular drone we developed here by ourselves. And let me see if I can show you because of this. Okay, just one moment. Let me see in the presentation mode. This is a fixed wing drone, and which can go up to more than 100 kilometers. It is, we can you see that my screen now? Hello. Can you see
Doctor,
my
are you
see your
sharing a
screen.
video? Are you sharing a video or the presentation?
Yeah, video, yes. But
I think you have to share screen again. Click share screen and select that video.
No, it is inside my presentation file. I think.
Okay.
And I think it's some problem. Maybe I will.
Yeah. Yep.
I think I don't want to waste the time. So I think that's my presentation. Maybe. Yeah. So should I stop sharing? Hello.
Yes, sir. Please go ahead.
Yeah. So this is just a last. Yeah. Okay. Thank you.
Sir, thank you very much. Thank you, Dr. Harika. We got a very informative information related to remote sensing and GIS. Now I am switching over to Dr. Sakti Suryavanshi. He is the moderator for the webinar, and with our experts, he will put up the question which is asked by some participants. So, Dr. Sakti.
There's some background noise is coming. Can you mute the mic? Somebody.
Thank you, sir, for this session. Thank you for imparting such knowledge for our participants. There are many questions asked by the participants. However, due to shortage of time, we are taking a very few questions from them. I want to ask, please, whether Zakaria sir is available or not.
Yes, I think he's available.
Yes, I'm here. Yeah, yeah.
Yes, sir. So there is one question related to you. Challenges that are related to watershed management, especially in the practical term, like for the countries like India.
I cannot really hear you very well. Yeah. Can you repeat the question?
Yes, sir. What are the different challenges that have been faced by, for watershed management in the countries like India or maybe likewise countries?
I'm not an expert of watershed management. Unfortunately, I cannot really answer this question because it's at the scale that I normally don't operate. Um, I know there are a few colleagues of mine that are dealing with the different watershed scale, and this is a hydrologic unit in California, but is somehow has to be intersected with the groundwater basin because in California the water managers are trying to consider the hydrologic unit holistically, so all connected, surface water and groundwater. And so there are administrative boundaries and hydrologic boundaries. So one of the challenges is how to operate the physical boundaries, so the hydrologic boundaries, regardless of the administrative boundary. But I'm not really an expert on those aspects. Yeah.
Thank you, sir. There's one more question for SP Agrawal, sir, if he is available. Okay. I think he is not available. So do we have Vishnu Chandra, sir? Okay, back to Hazarika, sir. Sir, one fellow, Elvin, has asked that what are the different challenges that have been faced in drone mapping? While doing the drone mapping, practically, what are the challenges do you face while doing it? Sir, I'm audible.
I think you have to unmute
Yes,
yourself.
yes. Sorry. Okay. So one problem with the drone is in India is a regulation is a problem for mapping or whatever. But technical issue is that the most of the drones which we are using for mapping are multicopters, which can fly only for 20 to 30 minutes only. So you cannot do large mapping. That's one problem. The second issue is you can use these fixed wing drones which can fly up to 1 hour, even 2 hours. But those are a little bit expensive. And so I think as price comes down, I think it will be easier. Also, processing softwares, which you need remote sensing knowledge, and also if you just give a image to a farmer after taking from drone, he cannot do anything. So some processing skills will be required. So now, like there are cloud-based platforms are coming up. You just upload the data, everything will be done, and you will be given the results. So this is one way these problems can be solved. But I think depending on the country, some country like China, they are quite advanced in drone technology. They are the leader in the world. They are using many ways. But I think in India, I believe that within next 2-3 months, drone law will be formally coming up, formally come into operation. And I think after that, it will take off in India. Thank you.
Thank you, sir, for the information. Thank you, sir. Now that's it for today for question answer session. Actually, we do not have this Vishnu sir and SP Agrawal sir available. So can Hazarika sir answer this question that the prediction and occurrence of pests and diseases, can we monitor or maybe we can get information about it using GIS or this drone method?
Yeah, I think pest and diseases is possible very effectively. It is possible because if you even satellite data or you can if you constantly monitor the NDVI, say 8 days, as I said, if there is a pest or disease, your greenness will be affected first, or water stress. Okay. So that can be captured using this multispectral or satellite data, depending on the crop also. Okay, if I was talking about rice or wheat, is a large scale crops. In UP, I was visiting your south part of Lucknow, in between Lucknow and Kanpur. I went to the field in 2013, and I see all rice at that point of time. So if this kind of large scale crop or wheat or sugarcane, satellite data is possible to capture this kind of anomalies or change anomalies in the field, and you can do that. The second one is with drone also. If you fly drone in a small level farm, a small scale, not a very big one, that can be also using this multispectral camera, Sequoia, which I have shown. It's easily possible. Even camera also, normal camera can be captured. Yeah.
Okay, thank you, sir. So that's it for question answer session. Over to Ashish sir.
Thank you, Dr. Suryavanshi. Now I would like to transfer Dr. Mukesh for the vote of thanks. Dr. Mukesh.
Yes, sir. Thank you, sir. Good afternoon, everyone. I am honored to have the opportunity to give a vote of thanks on the first day of the webinar. First of all, I would like to propose heartily vote to thanks of our chief guest, Mr. Vishnu Chandra, DDG and Group Head, Remote Sensing and GIS Unit, National Information Center, Government of India, New Delhi, for gracing webinar Seminar 1. Thank you, sir, for your very informative, interacting and thought processing address. Now, most importantly, I would like to thank our distinguished speaker, Dr. Daniel Zakaria, Agriculture and Water Management Specialist, Department of Land, Air and Water Resource, University of California, Davis, USA, Dr. SP Agrawal, Group Head, Water Resource, IRS, Dehradun, Manjul K. Hazarika, Director, Geoinformatics Center, IIT Thailand, for their valuable information in the field of agriculture, water resource using geospatial technologies. I also like to thank second day speaker of this webinar for their presence. Finally, I would like to thank all the audience for the participating in the webinar. Thank you very much, sir.
Thank you, Dr. Mukesh. It was great hearing our accomplished speaker, and thank you, everyone. It's been a pleasure being with you all today. If you have any questions or suggestions, please write us our email. Also provide us feedback. I believe it was a fruitful day, and we will continue tomorrow. Thank you and have a great evening. Thank you, sir.
Thank you, sir.
Thank you. Bye.